Where you from, by the way?
I'm in what was that?
Right.
Yeah. Yeah.
Any plan for? Are you staying longer? In a while, you know? Yeah, I'm gonna go to how long? Hawaii, yeah, another one? Tomorrow, to this trail. You're flying to Hawaii? Yes. We cannot go out.
Because it's just something.
Yeah.
It's just.
It's just 1 hour away and take all of it. I'm just saying, a few more years of cool. It's still a big dollar. That's fine, but you can go to technical, where's that means? Yeah, it's, yeah, I've noticed it. There was another of the same conference here, but it was in Africa. So I looked at the easy to be others, the workshop I love how they people are very nice to some. On February, yeah. So, but, so for the main conference, you have an abstract on February and then papers due on in March. So what we call in February, but then March, I think they get released and it is on March. And then probably around July. So the submission will be in July. So, yes, they are. That's around. I'll be watching. Okay, yes.
All right. I guess in this case, let's start the workshop. You can still hear me on Zoom. Can you confirm one last time?
Yes, we can.
All right, perfect. Thank you. Then let me share my screen. All right. So can you see my screen also?
Yep, all good.
Yes.
Perfect. Well, let me open up the chat just in case. All right. Okay, then I guess hello and welcome to the second workshop on maritime computer vision. My name is MaCVi. I'm going to chair this session. And yeah, this workshop obviously has been organized with the help of many people. So some of the organizing committee are just outlined here. So shout out also to Loise, Mathe, Janis, Mattia, and Arnold. And we will upload the Zoom recording. Hopefully this time we won't have any internet connection issues. Last year there were some problems, but in this case, I think it's not too busy, so internet might work, hopefully. And yeah, we will upload it, the Zoom recordings and also the slides. So check it out maybe after the workshop, especially for those participants coming from Europe, where it's midnight at the moment. All right. Okay, let's start off by having just a general motivation really quick. We've all seen these numbers again. So the open water covers 70% of the planet's surface. It accounts for 80% of international trade. And yeah, undoubtedly the oceans and other water bodies have a huge impact on all of our lives. But the industry and research around the maritime domain has historically been reliant on manual processes and human observation, which often are laborious, costly, and error-prone. Actually, as a matter of fact, just one funny story, 30 seconds. I met someone here at the conference 2 days ago, and he told me the process for the German Navy of how they identify ships. And what they would do is they would have binoculars and look at the ship, and then they would have like a really long encyclopedia, a book of ships that they know exist. And so they would manually compare the ship that they saw by their binoculars in the encyclopedia, and then they would like write down in a logbook by hand well, this ship at that time was there. So the maritime industry, I think, is very slow a little bit to adopt new technology, but this workshop is supposed to be a little bit a driving factor to also have a little bit more autonomy in the sector. And there are so many applications around in the maritime domain. You have autonomous boats and ships, autonomous search and rescue, maintenance, preventing of illegal fishing, monitoring of natural habitats, and so on. And yeah, the computer vision aspect of these things often is one of the most challenging one, because you have, yeah, you are just in such an unstructured environment, and the water itself, yeah, poses a lot of challenges, as we see in a second. And yeah, lastly, while there are many works done in this area within the last few years, they are scattered, it feels. And so this workshop also tries to aim, yeah, to bring together people from all sorts of maritime computer vision domains, hopefully by aligning interests a little bit and maybe having some transfer knowledge. And yeah, just to give you an associative mind map of what the maritime computer vision domain is comprised. So this is very similar to what I showed last year. So for example, the maritime computer vision domain consists of multiple platforms. You have airborne platforms, surface-based, satellite-based, underwater. You have so many different sensors from RGB, hyperspectral, infrared, sonar, depth, and so many applications, as I just mentioned. And many of these applications, they share the same challenges, such as water texture, lighting conditions. You have small sizes of objects, limited hardware, real-time requirements. I'm working with a startup also together right now, and just the movement of water poses a lot of challenge for stabilization and all that. And all of these applications, they raise a lot of, or a lot of computer vision tasks are created from that, as you can see in the bottom. And some of them we will cover in this workshop as part of papers, as part of competitions, and also as part of keynote talks. And yeah, then let me go to today's schedule. So we will have a very tight schedule today. We start off with a keynote from Shanzhan. I'm very happy that she can make it. She's in Europe right now. It's midnight for her, as I said. After that, we will have the competition summary and the presentation of the challenge winners. We'll have a short coffee break after that, and then we'll have two more keynotes from Danilo and Kakani. I'm also happy that they can make it. And then we will shortly go over the spotlight presentations of submitted papers. And finally, we'll have just a featured paper from MaCVi. And that's already it. We will have a poster session. It's a very small poster session, but feel free to come. For those people on Zoom, I'm going to leave the Zoom room open. So feel free to virtually meet up, virtually show posters. And yeah. So let's dive into the first program point already. And that's going to be the keynote from Shanshan Stoppel. She's the head of the group Optical Systems at Fraunhofer ISIT in Germany. And she has been working on MEMS technology for over more than 10 years. And I'm very excited to have you, Shanshan. Are you there?
Yeah, thank you. Thank you for the introduction.
Perfect. Do you mind sharing your screen?
Yes, I will try to do that. Okay, I think I will do that. So I switched off my camera to save some bandwidth, and I already share my screen.
Yes.
So okay, we have to go back to the first page one. So can you see my slides?
Yes, we can.
Yeah, okay, thank you very much. Yeah, Actually, I haven't seen ladies, but I think there are ladies also attending the workshop. Thank you very much to asking me, for asking me to give a talk. As you asked, I had a look on your website, and I found the different topics, so it just really encouraged me to come here. And my hope is also that we can, with our MEMS technology to join this topic and to find an interface. So find more partners for more topics. Yeah. Shall we start?
Yes, sounds good.
Okay, thank you very much. Yeah, good afternoon. Thank you for inviting me to give a talk, of the workshop. I'd like to present some ideas to bring MEMS-based devices into maritime applications. I took two examples of with me. First one is augmented reality projection system. The second one is a smart LiDAR system, LiDAR camera for underwater scenario. Yeah, thank you also for introduction about me. So I took the basic information about me. I finished my PhD thesis in University Kiel in Germany, and the topic was development of the piezoelectrical MEMS mirror. And my current focus is also MEMS-based optical systems, for which I'm heading the group MEMS-based optical system at Fraunhofer Institute for Silicon Technology. And the focus of our institute is all kind of silicon-based technologies. So for this reason, we possess quite large clean room areas and the most relevant past processings and also inline metallurgies. So if you are interested in silicon technology or our clean room facilities, you could use our website and our online tool, this one, to visit our clean room visually. Yeah, so we can then back to our talk today. As I said, I will give presentation about two examples, and we will go through the topics one after another. Yeah, the first one is this, the MEMS mirror-based laser projection. Before I introduce MEMS mirror-based laser projection, I'd like to invite you watching a video. It's very short film clip. You may notice the difference between such kind of video or a video played on your mobile phone. The screen used here is no normal display. It is paper. And how this works and what's the link to maritime application, I will explain in the next 15 minutes. Yeah, you can notice there is very high resolution, and you see some sparse line within the frame, but it is not because of the sparse light density. Rather, it's because this video was taken by a mobile phone, and regardless use what kind of camera it will occur. Uh, so the working principle. For construction such a laser projection system, we will need certain components. Firstly, we will need a RGB laser source, and we will need a MEMS mirror, and we also use an electrical unit for controlling the MEMS mirror and the laser source simultaneously. So then we can project arbitrary pictures and also videos. So how it works. Here's this MEMS mirror. It has a very small circular reflecting surface in the middle, and the surrounding arms, we call them MEMS actuators. these surrounding arms can move and can also move the reflecting surface in the middle. So if the moving mirror will reflect one laser beam, yeah, it reflected the different the one laser beam to the different positions one after another. If it is fast enough, this certain trajectories can fill a rectangle. So um, for this rectangle, we use a right laser. If you can imagine, we can synchronize every different positions with different color, with a purple color. We can then have colorful pictures. And if the MEMS mirror moves fast enough, and also the laser source can work with it, you can not only have one picture, you can have pictures one after another, and you will have a video. So it is how a laser projection works. Just for the understanding, the MEMS mirror not only reflect a rectangle, it can also reflect a line, and here is how it is to from one line to the second dimension and then to the rectangle, and this one can also work for the circular scanning. Yeah. So taking this basic knowledge, we are now stepping into the smart window idea. We need sometimes a flexible screen for interactive communication and navigation and also safety. So this screen can be the window, like where the pilot looks through. Such augmented and mixed reality systems are necessary. For this information, the pilot will not only look into the ship window, it can also have the additional information. And such kind of augmented reality and enhanced reality system are already targeted by example like smart glasses, which is a very key application nowadays. Um, but here we have a work scenario, and we would like have a sheer screen. So we use a window for us. So for the windows, we need a reflective, scattering, and also transparent film. And of course, we also need a working projection system. So it is not easy to fill a rectangle with a moving mirror because firstly, the light spots have to be very dense. So you see the difference between the different pictures. I give some technical data at the right side, but firstly we should concentrate on the pictures because they just tell us the difference. The four pictures are all realized by the same sample. So just by changing the driving frequencies, you can say there are different light density are realized. So actually, this one would be the best one, and this one is not very suitable for displaying a picture, for example. And secondly, also here some technical data, but we concentrate on this pulsation distortion. This comes from distortion or technically mechanic coupling, because the MEMS mirror, the reflecting surface needs to be driven in two axes simultaneously. So the two axes just take the energy and torque from each other, from one axis to the second one, and also then backwards. So this is a very strong mechanic coupling. This distortion is not usable for if you want to have a rectangular working area. So then as a summary, we need a MEMS mirror need firstly, high light density, and we also need a decoupling of two axes, but we also need a high mechanic efficiency. That means you give certain driving voltage, and the moving range of the MEMS mirror should be large so that you can have a larger screen, rectangle screens. And then we developed the MEMS mirror generation 1 with our patented designs and also patented glass dome. This glass dome can ensure a vacuum working environment for the MEMS mirror and also protect the device. If we compare the generation 0 and 1, we will see the difference. Firstly, we have here the much better light density, and also here it is a proper rectangle without any distortion. And it also has a very high mechanic efficiency. We can see this how to say the comparison. Already at very low driving voltage, we can already reach a high scanning angle. And yeah, on one hand, it is very good. Uh, yeah, it is good to have high mechanic efficiency, but on the other hand, the mechanic efficiency is so high that the springs twist to break. The springs twisted to break because the mechanical stress exceeds the bearable yield stress of the material. So that is the reason we worked further using FEM simulation for optimization our designs. And first one, we look into the springs, and we try to drive the mirror to a um, certain scanning angle, and we just measured or simulate the material stress. Since we use silicon as our basic material, silicon has a very it's actually very stable mechanically, and 1 gigapascal, it is quite good value comparing to the break stress of the material. So that is what we have done for optimization our designs for lower the stress. And of course, we also have to look into the line density if the mesh is still very dense, and to make sure that the MEMS mirror is also, if we use it for the laser projection, it does still have a very high resolution if we want to projection any videos or pictures. So yeah, then we finally we have reached the satisfying design with all good properties we need. We have a very good rectangle and also cubic, but we also say that the line density is compared to this picture, you can see the uh, yeah, very significantly improvement. So yeah, we use this MEMS mirror for our um, maritime use for projection pictures or also information on the screens. And we could test the laser projection system in a real ship and to verify the functionality. So it's the first story. And the second story is about the LiDAR camera. And here is a basic system knowledge about LiDAR camera. Also here we need a laser source, and we need a MEMS mirror to distribute the light in the space. And the targeting objects will reflect the laser beam so that the coming back laser beam can be collected by optics and measured by a photo detector. The measurement results of the photodetector will give information about the distance between the sensors sensor level and the target objects. So the user can actually collect a 3D data cloud from the environment and see the environment even if the light condition is very poor, because you don't need the light really for seeing everything. You just measured from one laser beam. And this working principle can be very beneficial for the underwater scenario, like for mapping or surveying. Yeah, moreover, we are even working on a more complete system under the project NeuroSmart. Here is our project name. We developed a LiDAR camera, and we also developed the analog neuromorphic accelerator. And in this case, and we also use develop AI-based recognition and also robot control. So how we could combine everything together. The LiDAR camera is something with it we can see. And then we have the data put into the photo detector, detects everything, and we have a data stream. The data stream is processed by the analog neuromorphic accelerator, which works as an edge device. And then the AI-based recognition is just like a brand to how to say, to analyze the information we collected. And then at the end, as a feedback, we also have the robot control to give all the result of an analysis of the information to our robot, where the robot works as our operator. Um, so yeah, the two short stories, and I think what we have done, we developed a MEMS-based device directly for maritime application. Even more, what I personally find more interesting is like the underwater LiDAR system or underwater robot, which we haven't realized yet, because we are working on the total system, combine the LiDAR camera and also the edge device and AR and also robot control. Is for industrial production line. But my hope is that we can find or we can identify the right partner for us. So we are quite looking forward to collaborations with partner for realizing of these ideas. And then I think I'm come to the end. And here is just a short picture from our institute. And here's my office. Here's just our clean room. And we have actually two clean rooms and a lot of labs. And yeah, thank you very much for your attention. And at the end, I'd like to thank the German Federal Ministry of Education and Research and also our Fraunhofer Gesellschaft for funding the two projects, Smart Window and NeuroSmart. Yeah, so that's the story I want to present today. Thank you very much.
All right. Thank you, Shanshan, for the very nice talk. You even had a lake on your picture in the very end, so that's definitely a relation to maritime domain there. Are there any questions from either the in-person audience? Yes, Janis, I guess.
Okay, just a quick question. So this is very nice system, and yeah, at the beginning I was asking, well, why not do LiDAR with it? Yeah. So, but my question is actually, so you're trying to make a bitmap picture, yeah, for the augmented reality, but actually for such augmented reality, the vector image would be enough, right? Which needs far lower frequencies. But you're actually doing bitmap one, yeah?
Yes, you can project it a bit, or you can project a video, what you need actually. But I'm personally also more interested in the underwater LiDAR system.
Okay.
But
So
yeah.
I have questions about this too. So this LiDAR, is this actual LiDAR time of flight, or it has geometric establishment of depth? Okay.
It's this time of flight, yeah.
So it's
time of
actual
flight.
time of flight. Okay. So and the camera does not have a MEMS mirror. So camera does not follow the actual laser source.
Yes, the LiDAR camera works also based on MEMS mirror.
Oh, so you have MEMS mirror for transmitter and MEMS mirror for recorder. Sorry,
Yeah.
for receiver.
Yeah.
Okay.
Yeah, for the
Okay.
yeah.
And last question, sorry. What is the maximum distance that you used this LiDAR for?
This is really very interesting question because we tested with different lasers, and
Okay.
our targeting is also to 200 meter because this is for
Okay.
automotive use, rather interesting. But we have to face a limitation because of eye safety. That is why I think underwater, maybe this point would be more tolerant. So maybe we can use some laser with a higher laser power so that we can use some different laser source than we have to use for the street and also for the industrial use. Um, I had looked into the literatures, and there are several, how to say, resource to present also this idea underwater LiDAR camera. But actually, I'm personally looking for the partners because
Okay.
the word is a totally another word, and we have to have a very competent partner. Yeah.
Because it needs krill water, otherwise there is too much
Yes.
dissipation, right?
Yes, and you
Yeah,
also
okay.
need above the water you need infrared or red, 905 nanometer. Underwater we rather use blue and
Blue or green, yeah.
the green light. The photo detector has also to work, and fortunately they work also with this wavelengths. So that is actually no technical limitations. Yeah.
Okay. Thank you.
Yeah.
That was it.
Thank you for the question. Yeah.
All right. Any other questions from the audience? Okay, in this case, thanks again, Shan,
Thank you very
especially
much.
for the time, and feel free to stay, but it's also fine if you want to go to sleep.
Yeah, so I really have to go to the bed because tomorrow is another working day. So
We'll
have
record it,
fun.
so
Yeah.
okay, perfect. Thanks
Yeah.
again.
Bye.
All right. So let's go back. To sharing the screen. I hope you can see that on Zoom. Otherwise, let me know, please. Yeah, that brings us to the second big point of today's challenge, which is today's workshop, which is the MaCVi 2024 challenge. So this year, as last year, we hosted multiple challenges based on UAVs and USVs, so drones and autonomous boats. And yeah, this is a similar motivation to last year. I mean, UAVs and USVs give rise to a multitude of different applications. So UAVs, for example, with maritime search and rescue, or with monitoring of large sea areas. For autonomous boats, I guess I don't have to tell too much. There's a lot of startups working in the recreational field to make boats more autonomous or to develop assistance systems, but also for monitoring purposes, a lot of unmanned surface vehicles are developed. And all of these applications, they need obviously more autonomy, and the computer vision aspect is a big aspect of them. And so far, only a few scattered benchmarks have appeared within the literature. And our aim of this competition as part of this workshop was to give more yeah, to show these benchmarks. And we want to promote the computer vision benchmarks via these challenges. And I want to mention that we have this year a couple of sponsors, which is Sentient Vision from Australia, Luxonis from Europe, and Lookout. They're sponsoring prizes and data. And the challenges we look at this year are different from last year. So last year we had 4 competitions. This year we have 5. We have UAV-based maritime multi-object tracking with re-identification. So last year we had the same competition track just without re-identification. Then we have the USV-based obstacle segmentation and embedded obstacle segmentation. Because of the feedback of some people, we do have an embedded competition track for the first time, because that was one of the main, let's say, criticisms of other challenges, that everyone is just submitting methods and object detectors and whatnot, too big to deploy anywhere. And this time, we, with the help of Luxonis, we have another challenge track. And then we also have USV-based maritime obstacle detection, which is similar to segmentation, just with bounding boxes. And a new data set, which is USV-based multi-object tracking, which is actually a data set from a startup that approached me. And so this is an actual, let's say, industry data set that's being used. And yeah. And to put this into context again, so we are dealing with the airborne and surface-based platform. We are on the RGB sensor front only. Applications can be search and rescue or navigation, but technically it can also be like more downstream applications. We face most of the challenges that I mentioned already. And yeah, just to give you an idea about the protocols and rules of this challenge. So the challenge was running from September 20th to November 3rd. And participants could download datasets, evaluation, visualization toolkits via our new MaCVi workshop webpage. So actually this webpage is a new webpage, which is not just for a workshop, but we want to do it more as an initiative for the maritime computer vision domain. So our aim is to be a hub essentially for all maritime computer vision research. So feel free, if you have anything that you want to promote, just approach me and we'll put it on there. And yeah, then let me finish the slide. And then, so the participants were asked to upload their predictions for some of the challenges. For some other challenges, they were asked to upload ONNX files, so neural networks. And on the web server, they were compared either against the ground truth predictions, or the neural networks were evaluated on the respective test data sets. And participants could upload once per day. We received roughly 200 submissions, and the winners of each track were featured in the challenge summary paper. And some of those things we will discuss now, but a lot of details we won't discuss. So I will refer to the challenge summary paper if you're more interested. And again, we have Sentient Vision, which sponsored a prize for the best team of the UAV-based multi-object tracking with re-identification challenge. That's actually a GPU, as we will see in a second. And Luxonis sponsored the prize for the best team in the USV-based embedded obstacle segmentation challenge. Yeah, we'll also see about that in a second. And we'll dive right in with the first competition. The first competition was the UAV-based. Sorry, your question first.
Slightly critical remark. I mean, you motivated the competition for the first slides, and this was not all valid. I mean, all computer vision researchers, we know what the amazing benefits of this technology are. But I thought also as researchers, it is important that we remember that some of the things we do can also have negative consequences. And because of that, I would like to mention that an advocatus diaboli would very easily and validly say that this is weapons research. Right. I mean, I don't mean to validate what we're doing here. I didn't know it's all has its history. We need to remind ourselves from time that people might use it also for things that are maybe a bit controversial.
Okay. All right, thanks for the comment. So just for the people on Zoom that did not catch it. So there was an important critical remark from the audience about the use cases of these challenges. So I mentioned some of the applications like search and rescue, and also autonomous driving, for example. But it was rightfully noted that it can be abused or used also for military applications, and we should always keep in mind that these applications exist, if I summarize it correctly. And to comment on that, I definitely agree. This was actually one of the main motivations why in the first iteration of the workshop we had SearchWing. This is a German-based nonprofit organization which specifically tries to do search and rescue and has a big user base and tries and makes aware of the fact that a lot of stuff is happening, for example, in the Mediterranean Sea. And we had a panel discussion also with them last time. It's actually on our workshop webpage. I'd highly recommend going over that. I think in this workshop iteration, there's not a particular focus on, let's say, the ethical consequences of it because we don't have a panel discussion. But yeah, I agree. It's definitely an important point. Mind. All right, to go back to the first competition. So in this case, UAV-based maritime object tracking with re-identification. So this challenge track was extended from the Sequence-C multi-object tracking benchmark. This was published as part of MaCVi 2022. And it's essentially the same data set, except for we relabeled it. So we corrected a lot of annotation errors, but we also extended the labels to include long-term tracks. So whenever an object leaves the scene, it will have the same ID whenever it enters the scene again. And we treat, again, this challenge track as a single class benchmark. And again, each frame comes with metadata. And we evaluated the submissions of participants with the common tracking metrics. So HOTA, MOTA, IDF1, and so on. And the determining metric for winning is the HOTA, the higher order tracking accuracy metric. And we also required participants to report the FPS, hardware, datasets used. And we also gave them public detections, which they were not required to use, but may have helped some people for an easier start. And as you can see on the right-hand side, for example, if we compare the different videos in the test set before re-identification, which is the first column, and unique IDs after we relabeled them. And you can see that for some videos, quite a few reappearances exist. And yeah, this was like the novelty about this challenge track. And so we received 49 submissions from 18 different teams. And yeah, as I said, we provided one baseline also, tractor with this motion model and a faster RSNN ResNet 50 backbone. And in our analysis, we focus only on the best 3 teams. And yeah, those are the best 3 teams. So this is the MG mod, the tracking by detection, the ReID tracker C. There's not too much, let's say, surprises in terms of what data they trained on. Essentially, they pre-trained on COCO and transfer trained then on the Sequence-C train and validation data set. And more surprisingly, maybe, is that there's not a clear trend when it comes to the underlying detector that they used. So the first method uses a one-stage detector, fairly new YOLO V8. Then the varifocal net, which we saw last year, also a two-stage detector, and also a SWIN transformer in the third case. This was not an embedded challenge. Obviously, again, this is reflected in the FPS, so this is not really running in real time, especially not on embedded hardware. And if we look at the performance of these 3 methods, then we see that it's very close for the first 2 submissions, so MGMod and TBD. They are only 0.0. 0, 2 HOTA points from another. And especially in MOTA, it's the other way around. And that's a bit unfortunate, I guess, for TBD. Especially, for example, because TBD has the lowest number of ID switches, which is very similar to the first place. But yeah, the why re-ID tracker C is so much worse in HOTA is probably because of its incapability for associating objects nicely, which is also reflected like in the much higher number of ID switches and fragmentations. And even though like the recall and precision of the third method is the best, yeah, it fails at associating objects. And yeah, the re-ID tracker C did not have a camera motion model, and I think this is one of the reasons why they performed worse in like associating objects, right? So the IDF1 is much worse than HOTA. And yeah, yes.
Number of items here, the number of items, and you the album picked out.
That's the number of ID switches, meaning incorrectly giving an ID. For that we have to go back. If it's listed here. So we have 403,000 annotations, but this includes train, val, and test. The distribution is very similar, so you can do the math. It's proportional to that. So 19 out of this, roughly.
Answer there, I asked, how many unique maritime objects are there?
Okay, sorry then. So those are the test videos from 0 to 21. There's some missing. Exactly. Right.
And fragment-based tracks.
It's the number of an object is tracked correctly, but then it is lost. Essentially, it's not detected anymore in one frame, and then we would count it up one. Right. All right. And yeah, some of the errors you also see in these images here, or not. It's really small, but for example, this video sequence of 3 consecutive frames, this is, I think, tracking by detection method, which fails to track this swimmer over here. So there's a small blue swimmer. We do a slight panning of the camera, a heading change, and so it is lost in this frame completely, and it's getting a new ID in this frame. But that is a common error that we also saw last year. So like the dynamic nature of the camera changes has a big impact on the association accuracy. And that's not really new. What's new this year is more like the bottom line, which is the re-identification aspect. Yeah, I'll show a video in a second also, but this is essentially also like 3 frames. They're not consecutive, but like with a distance of like 1 second or 2 seconds. In the beginning, we detect this boat correctly. Then it is lost just because we move the camera, the drone somewhere else. And then the same boat appears with a different label, just because it's really hard to distinguish these boats because of their similar appearance. We can see that in the video also. Here. So this in the beginning, this is like the purple boat, like the purple detection of the boat. So we lose it. Keep in mind, like this red boat points towards this other boat, and whenever this appears again, it has a brown label. It's a different ID, just because, yeah, the appearance is pretty similar, and that's one of the challenges maybe generally in aerial multi-object tracking with re-identification. Appearance-based re-identification is pretty hard sometimes. In this case, those are nearly identical boats. And so the question is, how do you really solve that? And one of the answers, maybe actually in one of the methods we'll see, like one of the winners, they actually try to leverage metadata, which give you an understanding of this scene. So you can kind of know where objects were seen in the real world, and you can back reference that later and maybe build on that information. Right, so as a summary for this challenge track, I haven't talked too much about the first part, which is hard detection is a major source of error. So this is still correct. We're in the aerial domain. Objects are really small. We have a lot of small swimmers. Some of them are missed, especially if we have a very acute angle, then at a very far distance, objects are really small. So that's really hard. In that case, still fast camera movements are problematic still. And we don't really we don't really have a way of dealing with it. If we fastly switch, then we have a lot of blurring in the image, but at least we can re-identify objects afterwards, hopefully if the method is good enough. And yeah, re-detections with similar objects is difficult. So how do we leverage that really? Because appearance-based methods may fail in this scenario. So do we really need a more holistic 3D understanding of the scene we see? And I would say yes, but yeah. And obviously the general criticism again is all these submissions have low FPS. It was not a requirement of the challenge. Obviously no one adheres to that, but we'll have to, I think, create challenge tracks that are more constrained on this end also. And with that, I wanna again announce the winners. So this is an error here, unfortunately. So this is second, this is third. But yeah, the first place is MGMod method, which is from Chen Yan Yang, Xiang Wai Huang, Zhongyu Yang Heng Zheng Kuo, Yimai, and Yang Neng Huang. And yeah, Sentient Vision sponsored the first prize. So you win actually a GPU. Are you here, Chen Yan Yang? You're here? Why don't you come to the front real quick? So I just got sent this package from Sentient Vision to Hawaii. And yeah, so that everyone sees we have a 4090 GPU. Well done. Yeah, you might want to put it. All right. And yeah, unfortunately, there's only one place that gets a prize this time, but I want to shout out, obviously, the other places which were really close with a strong performance tracking by detection, Daniel Stadler and Lars Sommer, both of which cannot be present today. And then Re-Eddy Tracker C with Kerr Huang, Aigur Zheng, Waitu Chong, Kanopan Lertni Fan, sorry for butchering your name. Yongxi, Feng Chen, Yan Li, Zepeng Wang. Also, congratulations to you guys. Really well done. And we'll take a picture later with Chen, Yan, Yang. All right. With that, are there any questions for the UAV-based maritime object tracking competition part from the audience in Zoom or in person? Nope. With that in mind, then we go to the second tracking challenge. So in this case, we have a different domain, a different platform essentially. So this is USV-based maritime object tracking. So this is a new multi-object tracking dataset from the viewpoint of unmanned surface vehicles. I say unmanned surface vehicles, but what I also mean is just generally from the viewpoint of boats. And this is a data set that was sponsored by Lookout, which is a startup from Boston. And this is actually one of their boats that they actually deployed their camera on and what they see and where they want to do computer vision on. And the data set is comprised of classes, boats, buoys, and in this challenge, we only considered the boat detection essentially. It's a short-term tracking challenge. And it's very crowded. So maybe I'll show this video real quick. So as you can see here, it's a very short clip. We have like a lot of occluded boats, right? And very many boats in a very unstructured environment. You don't really know where a street is or the safe passage track of the boat. And yeah, this is one of the main challenges. You have like many different sizes of objects, but they all cluster around the horizon line, right? Since you're on a 2D plane almost. And so the question is if there need to be particular methods, let's say for the detection part even, to really leverage the information that we're on a 2D sphere, because it seems to me like all the competitions we had so far, they just put like standard object detectors on there, which is fine, but it somewhat like doesn't really leverage the fact that we have a specific maritime scene. But in this case, we cared about tracking and detection. And this data set was, we only gave you the test set, essentially. We didn't give you train sets, so you were supposed to train on another data set, for example, Lars, which was one of the other challenges. And yeah, some of the challenges you saw that I just mentioned, you see also in these statistics. So you have, these objects live for a long time. So for example, the average lifespan of an object was like for 500 frames. So you see it for a long time and objects are occluded. So you still have to track it, right? Even though another boat is before that. And that was like one of the main challenges. And yeah, the evaluation protocol for this challenge, again, was the same evaluation protocol as we had also for the other tracking challenges, HOTA, MOTA, IF1, and so on. And again, the determining metric for win was HOTA. And obviously, we required participants again to give us more information about that. So this challenge track started a little bit later, just because we didn't get the data early, unfortunately. But we still received 23 submissions from 8 different teams. Again, here are the best 3 methods only. And yeah, so we have the detector ensemble, ReID tracker C, which is the same team as from the other track, and DLR boat track. 2 of the methods use a single stage detector, YOLO V8, with some modifications, and 1 uses a swim transformer. So that has been a trend for sure, that more and more people always also use transformers in our domain. And again, FPS obviously tells you again that we need to impose some restrictions for future competitions. And we will have it for the other challenge track though. And you can see the performance result. We see that the detector ensemble has 21.5 HOTA, closely followed by ReID tracker C, and DLR trailing that. And we can see already that this performance is much worse than it is for the other challenge. So for the other challenge, we had HOTA values up to 60, and here it's only 20. And the reason for that mainly is just because of the domain gap. People trained probably on Lars and other data sets. They will talk about that later. But yeah, this is probably the main reason, the domain gap. And obviously also the occlusion factor is a big part. I hope we'll see that later when the competition winners talk. And yeah, with that, I want to announce the winners of this challenge track. The first place detectors ensemble, which is Xiang Wai Huang, Cheng Yin Yang, Zhongyu Yang, Sheng Yao Quan, Yuan Hao Hu, Yang Neng Huang. Congratulations to the first place. Then the second place is ReID Tracker C, again with Kea Huang. I'm gonna just pronounce the first name now. Aigyo Waitu Kanok Pan Yun Feng Yan Sepeng. Congratulations to you guys also. And the third place was DLR Boat Track with Angel, Boya, Alexander, Antje, Yannick, Felix, Edgardo. Congratulations to you guys, and thanks again for Lookout, also the startup that we got the data from. And yeah. Are there any questions for this challenge track? Nope. So again, or not again, but all the winners, they get certificates online. If you need one, just drop me an email and you'll get one. I don't have physical copies right now. Yeah. I think with that, we go to the obstacle detection and segmentation challenges. And I will hand over to Loise, if I'm not incorrect. Loise, are you there?
Hello, can you hear me?
Yes, we can hear you fine.
Okay, good evening from Europe. I will share my screen. Okay. Are you able to see?
Yes.
Okay, great.
But
Hello.
let me switch first on my end. Mhm. Going up. Mhm. 1 second. Like that. I'm having trouble switching to your view.
You
Really
can't see
know.
my screen, or
I can see your screen, but I need to switch to the presenter view. Sorry, I need to like so that people can see it also here in person, but it wouldn't let me. It won't let me switch to it. I don't know why.
maybe I can try to stop and do it again.
Yeah, maybe stop it and then. Oh, there it is. Yeah. All right. Perfect. Thanks.
Now it's
Yeah.
gone, and now it should be back.
Yes, now we can see it also here.
Okay,
Thank you.
perfect. Great. So I won't touch anything, just
All right.
okay, great. Okay, so my name is Loise, and today I'd like to talk about the results of our challenges on obstacle detection and segmentation for USVs. So this year we decided to host 3 different challenges in this domain. So these are the obstacle detection challenge, the obstacle segmentation challenge, and finally this year we also have one new challenge, which is an embedded challenge, which we are very excited to talk about. First, the purpose of all these challenges is to develop basically scene parsing methods mainly for the purpose of obstacle detection and obstacle avoidance in unmanned surface vehicles. So this year, for the first time, all the challenges are based on the newly released LARS dataset. So this is a dataset that we recently presented at MaCVi, and it's currently the largest and most diverse maritime panoptic dataset, which contains roughly 4,000 per pixel labeled scenes. And our goal with this large dataset was to evaluate the robustness of current methods to a wide variety of different scenarios, different challenging conditions, and different obstacle types. So as you can see in the image here on the left, the scenes that are included in this dataset are very diverse and have been captured all around the world. We also provide the panoptic annotations, as is shown here on the right. So this includes the background segmentation of sky, obstacle, and water components. And then we also provide the instance segmentation labels for individual obstacles, dynamic obstacles that are floating in the water. So these kind of annotations enable us to tackle a wide variety of tasks. So this includes stuff like object detection, semantic segmentation, panoptic segmentation, and so on. So this year, the first challenge that we hosted was the USV-based obstacle detection, which has a very simple setup. So the goal here is to basically detect all the obstacles in the water using bounding box predictions. So here we don't care about the class of the obstacles, just the location and the bounding box of the obstacles. So we had a bit of a discussion whether or not to include the obstacle detection challenge at all this year, because the new data set is mainly a segmentation data set, and a lot of the field of maritime scene parsing is moving towards the segmentation approaches, but we still decided to keep it because object detection is a very core task of computer vision, and especially for these practical applications of marine robotics, it's able to address the task of obstacle avoidance in a quite direct manner. So as I mentioned previously, we used the Lars dataset in the challenge, and because the dataset is a segmentation based, we had to first convert the ground truth to be able to use it for detection methods. So what we did is we basically ignored all the static obstacles. We ignored the water segmentation, the sky segmentation, and we only focused on the dynamic obstacles. These are the obstacles that are in the water. And specifically, we grouped all the different obstacle types into a single class, just obstacle. And to get the bounding boxes of these obstacles, we just looked at the instance segmentation mask for each obstacle, and we converted it to a bounding box. So it's a very simple setup, and so the participants could use the training set of Lars to train their methods, and we also allowed additional data sets to be used. And then for the submission, they had to predict the bounding boxes of the obstacles on the test set and submit it to the evaluation server. And then we had a very simple metric for evaluating these methods, which is based on a previous benchmark MODS that was used for maritime obstacle detection. And it basically considers the F1 score. So the F1 score is computed by counting the number of true positive, false negative, and false positive detections. And the way we obtain these true positives and false positives is by checking all the bounding boxes in the ground truth and seeing and computing the intersection over union with the prediction, with the predicted bounding boxes. And if this intersection over union is larger than a certain threshold, in this case 0.3, we count it as a true positive. Otherwise, we count it as a false negative. And then in addition to this, we also ignore all the obstacles that are predicted inside the static obstacles, because we didn't include it in the during the training. So all the obstacles that are predicted in the static obstacle regions are actually not counted as false positives. Yeah, so basically this F1 score is then used to rank the methods, and here are the results of the submissions. So in total, we received 34 submissions from 6 different teams. And we also provided one baseline, which is the YOLO V7 method, which achieves the F score of approximately 18%. We're very happy to see that all of the teams managed to beat the baseline by quite a large margin, especially the top methods. For example, the winning method, which achieved an F score of over 50%, which is a very significant jump from the baseline that we provided. So the top 3 methods, 2 of them are based on the YOLO V8 architecture. So this is the first placing method and also the third placing method. And the second placing method is based on a data-like architecture. And here one of the most interesting things in these results is that the first placing team not only managed to beat all the other teams by a really significant margin, by almost 8% of F1, but they managed to do this by using a much more efficient method than all the other teams. So they achieved an FPS of 40 on a quite dated hardware, especially compared to these other methods which use much more powerful hardware. So stay tuned to see the author presentations to see how they managed to achieve this. Okay, so another thing that we noticed that mattered a lot in these methods is what kind of data set they used. Specifically, if we take a look at the first 2 placing methods, we see that they all used additional data during training. And specifically the first placing method used a lot of different training data. So this includes stuff like COCO and also some more obscure data sets, like they used their own collected data set to improve their results as well. The second placing method also used some additional data sets like COCO and Objects 365. And finally, the third placing method used some interesting data augmentation techniques to also extend the data set. Okay, so with this, I'd like to announce the winners of the obstacle detection challenge. And these are in the third place, we have the German Aerospace Center with their method SCAT YOLO V8 plus CBAM. And the authors of this method are Boria Carrillo Perez, Alexander Klein, Antia Alex, Edgardo Solano Carrillo, Felix Sattler, Yannick Steiniger, and Angel Bueno Rodriguez. Congratulations. In the second place, we have Fraunhofer IOSB and Karlsruhe Institute of Technology with their method CodeEther. And the authors are Andreas Michel, Wolfgang Gross, and Martin Weinmann. And finally, in the first place, we have the team from University of Zagreb, Faculty of Electrical Engineering and Computing, with their method YOLO V8 extra large. And the authors of this method are Matej Fabianic, Magdalena Shimunec, and Nadir Kapitanovic. So congratulations to all the winners, and all of these methods will also be presented in the next session, so stay tuned for that. So now let's move on to the second of the 3 challenges, which is the USV-based obstacle segmentation challenge. So here the setup is quite similar, but instead of predicting bounding boxes for the obstacles, we instead have to segment the input image into 3 semantic components, which are water, obstacles, and the sky component. And the one that we are most interested in is this obstacle component. So similarly to before, participants were asked to upload the predicted segmentation masks for the test set, and we use the following metrics to analyze these results. So first we use the mean IOU metric, which is a standard segmentation metric, but is very general, so it doesn't kind of detect all the nuances that we want to be able to evaluate that are important for the obstacle avoidance and detection. So to do this, we also employ an additional metric, which is focused on the detection of dynamic obstacles. So here we count the number of true positive, false negative, and false positive detections, similar to before, and then we summarize this performance by using the F1 score. And the final metric that we use for ranking the methods is a combination of the mean IOU and the F1 score, and we call this metric quality. So let's take a look at the results. So in total, we received 49 submissions from 7 different teams, and we also provide 2 baselines, specifically the KNet baseline, which was the state-of-the-art method on this data set at the time of publication. And we also include DeepLab, which is a tried and true segmentation method. We're happy to report that 4 of the teams managed to beat all the baselines. And what's interesting is that all of these 4 methods are based on a very similar architecture. So they use mask-to-former architecture. Sorry? Okay. So all these methods use the mask-to-former architecture, which goes to show that this is a very powerful method to solve this kind of tasks. But despite that, the differences between these 4 approaches are quite significant, as we can see in this quality metric. So we decided to also analyze how these methods perform under various conditions that are present in the large data set. So here we show various different environment types, illumination, different amount of reflections, and other adversarial conditions such as fog, dirty lenses, and so on. And with the dashed line here, we show the performance of the baseline method, so you can easily see which of the methods managed to beat the baselines in which categories. So here we note that the top 3 methods show remarkable robustness to a lot of these different conditions that are present in the large data set. Especially, we saw large improvements when looking at night scenes, for example here, or when scenes have a large amount of reflections, as we can see here. And one thing to note is that the best performing method, which is called swim squared, is able to beat the baseline across all of these conditions, which is quite remarkable. Okay, so maybe to show this, improvements in a more practical, qualitative example, we have an input here. We have an input image where there's a lot of reflections, so it's hard to tell, to differentiate here between this barrier and the reflections. And as we can see, the baseline method struggles to correctly segment this barrier. However, the top performing method here is able to accurately segment this water barrier. Similarly, here we have a nighttime image, which is quite which has quite low visibility, and it's hard to segment anything from this. And the baseline fails quite significantly here, so it doesn't detect the boat that is present here, but it's hard to see. And it also fails to segment the static obstacles in the background. However, when we take a look at the top performing method, we can see that the boat is clearly detected, and also the static obstacles in the background are much better segmented as well. Okay, so with that, I would like to announce also the winners of the obstacle segmentation challenge. And these are: in the third place, we have the team from Dalian Maritime University with their method MaCVi Mask to Former. And the author of this method is Yuan Feng. In the second place, we have the team from Hong Kong University of Science and Technology with their method TransMarie, with the authors Tuanan Wu, Hai Nguyen Tuong, Tan Sang Ha, Quan Dang Pham, and Sai Ki Tiong. And finally, last but not least, in the first place, we have the team from University of Cagliari and their method Swim Squared with the authors Luca Zeda, Andrea Lodo, and Cecilia Di Roberto. So congratulations to all the winners as well. And the authors of the top 2 methods will also present their methods in the next session, so stay tuned. So now it's time to move on to the last challenge of the day. And for this, I'd like to invite Mattia, who knows a little bit more about this challenge, to tell us all about it.
Yeah. Hi everyone. Can you hear me well?
Yeah, I think we
Yes. Yes.
Great. Yeah. Hi. So my name is Mattia. I present Luxonis. I represent Luxonis, and I will present you the embedded challenge. So basically, the embedded challenge is an extension of the non-embedded obstacle segmentation challenge, and thus has the same goal of segmenting the input image into water, obstacles, and sky components. In addition to that, we want the methods to be suitable for deployment on embedded devices. And for the device here, we chose our next-gen device, which is based on Robotic Vision Core 4, and will be released in the middle of this year. So if we go to the next slide, please. Yeah, the evaluation was more or less similar to the evaluation of the obstacle segmentation challenge. So we use the same quality metric, but we impose an additional constraint of the methods having to achieve at least 30 frames per second on our Robotic Vision Core 4. So I'll briefly talk about the evaluation protocol that we did. So we required that the methods we set a set of extra requirements that we needed to be able to kind of compile the models on our end and make the predictions. And so those extra requirements, for example, include a fixed input shape and the same, and the images need to be processed in the same way. So we kind of use ImageNet mean and scale to normalize them. In addition to that, we require the models to have a single output, and then we also require them to have a static graph so that we can export them to Onyx. We also released a set of supported operations before the challenge, so that with this we ensure that all of the models on our end can compile. Yeah, if we can go to the next slide, please. Yeah, so we received 35 submissions with multiple submissions per team, and this includes 8 baselines from us, from the organizers. And if we can go to the next slide, we have the full table there. Yeah, so we can see the full table here, and so we can see that the best method achieved results comparable to our best baseline, but being much faster, almost 10 times. One kind of important thing to notice here as well is the result kind of a large drop compared to the winner of the non-embedded challenge. So the swing is squared. And this mainly stems from the constraint of a smaller input shape. And so if we can go to the next slide, Luisa. Here we show this phenomenon where you can see that there can be obstacles that are very small, such as a fleet of boats or like chunks of ice. And when images are kind of downscaled, the methods have a problem by recognizing those and correctly classifying them as an obstacle. In addition, the methods might have similar limitations as those in the embedded challenge, where they might struggle in presence of wakes and glare. But I would refer you to the challenge summary paper for that. Yeah, if we go to the next slide. So yeah, to announce the second place of the embedded obstacle segmentation challenge belongs to the Diane Maritime University with authors Yuan Feng and Lizing Tian. And then the first place belongs to the University of Information of Technology from Vietnam National University by author Nguyen Van Tien. Yeah, congratulations to everyone. The first place will receive a store voucher from us because we haven't released the device yet. And yeah, we'll get in touch with the winner.
Okay, so I guess this is it from the 3 challenges that we were presenting here. So this is the time to ask any questions about all the 3 challenges, if there are any.
So no questions from
Okay.
the physical participants? And I guess there's nothing in the chat either. All right. I guess in that case, thanks, Mattia and Loise. And we'll go to the winner presentations of the individual challenges. Let me pull up slides. Okay, so I'm going to ask now the participants of the individual challenges, if they are there either in person or virtually, to present here. And yeah, we'll start with the first talk, which is the first place of UAV-based object tracking with re-identification, MGMod. Here's Yang Wei. You have connected to Zoom. You connected there via Zoom, so you just need this.
No, I can show.
Okay.
We'll change time.
Okay. You mute it or?
So like,
Okay.
yeah.
Okay, so hi everyone, I'm Shen Hong, and today I'll represent the information processing lab from the University of Washington and present our first place solution for the UAV-based multi-object tracking with re-identification, and also our workshop paper, See You Later, a meta-guided long-term re-identification for UAV-based multi-object tracking. The challenges in a UAV-based MOT can be briefly categorized into 3 categories. First is the rapid movement of the drone, which is common as the drone is constantly moving. And second is the sudden gimbal change of the camera, as the direction can cause both detection and tracking to be unreliable. And lastly, the long-term re-identification problem, which is also the main focus of this year's challenge. So we try to associate the identities of the targets, even they leave and re-enter the camera field of view. And this is a brief summary of the C-C MOT dataset, and the challenges details are presented along with various testing sequence that showcase the data's diversity in altitude, camera angle, and drone motion. And a total of 21 unique sequences and around 54,000 image frames. And the final evaluation metrics for this MOT challenge is HOTA, and we also have the MOT clear metrics. And now I will talk about our method. We propose a method called meta-guided MOT or MGMOT, which utilizes the metadata including the GPS location and altitude of the drone, the gimbal pitch and heading direction to estimate the targets from image coordinate to the 3D world coordinates. We first adopt a simple tracking by detection method using YOLO 8 as the detector. And we use BOT sort as our primary tracker to obtain the initial tracking results. And later we use the information to conduct two tracklet refinement steps, including the short-term reunification and long-term reunification. And the short-term focuses on the tracklets that did not leave the image at all, while the long-term focus on those targets that leaves the camera view and re-enter. And the reunification association cost is simply based on the distance of the object in 3D coordinate. And we use these two post-processing to connect those fragment tracklets and increase the tracking accuracy. And we also use several different methods, including bidirectional movement, extrapolation, and matching threshold expansion. So we gradually increase the matching threshold so we can start with those fragment targets with closer distance, and then we gradually goes to the targets that has larger distance for association. And for our results, we propose a meta-guided MOT and showed promising results on the test set of this year's C-C MOT dataset. And we're ranked first place in the UAV-based MOT challenge in terms of the HOTA performance. So after the UAV-based MOT, I'll now talk about the USV-based multi-object tracking and our first place solution. Similar to UAV MOT, the USV-based MOT track also aims at tracking the object on the sea surface. And the main difference is that the camera is located on the unmanned survey vehicle instead of the drone. So because there's no training data provided, we leverage the large dataset mentioned before. And we use this dataset to train a YOLO 8 object detector. And the large dataset is like introduced before. It's an object detection dataset that has multiple different objects across different water scenarios like lake, river, and sea. And in our experiments, for most of the scenario where those boats are very far away, the detector trained on the large dataset can actually do better than the COCO pre-trained YOLO 8 model. So you can see we have a lot of detection, true positive detection on the large trained YOLO 8 model. But for the COCO trained YOLO 8 model, you can see there's a lot of missing detection. But however, we noticed that when the boats are very close, the large dataset trained YOLO 8 does not perform very well. You can see we have a lot of missing detection when the boats are very close. While the COCO model can actually do pretty good when the boats are far, when the boats are close to the camera. So we assemble the detection results from these two models in our tracking process. And we also use BOT sort as our tracking algorithm. And for this track, we do not use any, because there's no metadata, so we do not use any metadata post-processing for this track. So our whole pipeline is an online method. And in conclusion, our method's final performance is also ranked first place in HOTA on the final leaderboard of the USV-based MOT track. And that's all for my presentation.
All right, thanks, Ivan. Are there any questions? Otherwise, I'll have a question. So you said that Lars is better for far distance and Coco better for close distances.
Yeah.
Are you using both at the end of the day, or did you use only one?
Yeah, so we have different experiments. So it turns out that for some of the sequence we use the Coco Chen model, and some of the sequence we use Lars Chen.
Right, makes sense. Right, thank you. I do have an annoying background. Wanna somewhat remove, but let's just do that. All right, with that, I'll ask the second place of the UAV-based object tracking with re-identification team, but I think they can't be here today, so that's why we'll just play a video.
Hey, Benjamin, we can't hear the sound over Zoom.
All right, thanks for letting me know. Sorry.
Hello,
Now?
I'm Daniel Stadler from
Yeah,
Fraunhofer
now it
IoT.
works. Perfect. Thanks.
All right, thanks for letting me know.
I will present this joint work with my colleague Lars Sommer on tracking by detection for maritime object tracking. As the name suggests, we follow the tracking by detection paradigm and perform detection and tracking in an online fashion. In addition, we apply a re-identification module for long-term tracking and further post-processing. I will now briefly present the single components. As detector, we leverage varifocal net with ResNet 50 as backbone and pre-trained weights on MS Coco. To train the model, the C-drone-C object detection V2 dataset inclusive validation split is utilized. Multiple scales are applied both during training and inference, and the 5 classes of the dataset are used. To suppress false positives, detections with an aspect ratio above 5 are removed, and an interclass non-maximum suppression is performed. For the tracking task, a two-stage matching similar to BiTrack is done. First, high-confident detections are associated before the low-confident detections are matched to the remaining unassigned tracks from the first stage. As motion model, the NSA Kalman filter is applied. We introduce an occlusion-aware initialization that forbids the start of the track on already occupied areas to prevent ghost tracks. Furthermore, orb features are extracted and matched in each frame to compute transformation matrices for camera motion compensation. To enable long-term tracking, we introduce a re-identification module. The model from BotSort is adopted to extract appearance features for each track box. Then, a hierarchical clustering based on the cosine distances between the track's mean feature is performed, whereby temporal constraints are considered. As additional post-processing, short tracks are removed and the remaining tracks are linearly interpolated. Achieving the second place in the multi-object tracking challenge with only a small margin to the winner shows the competitiveness of our framework. Compared to the best entry, our detection accuracy is higher, while the long-term re-identification accuracy is worse, which is indicated by the smaller IDF1 score. We think that the reason for this is that we do not use any meta-information in our approach. Thus, incorporating such information to improve the long-term association capabilities of our framework is a promising direction for future work. Thank you for your attention. If you have any questions or comments, feel free to send me an email.
We cannot hear you.
Now I'm going to the sorry for that. I'm going to the third place of UAV-based object tracking with re-identification. So the re-ID tracker C, and they're also going to present the second place of USV-based object tracking with their same named method. Are you there, Care Wang? If not, we're gonna play a video as well. All right, let me know if you're there. I'll play the video now.
Hello, everyone. My name is Carl Huang. I come from Lenovo. I am very pleased to have this opportunity to present our team
Can you hear it in the room, actually? Yeah.
challenging solution. RID tracker for C scenario, multi-object tracking in maritime computer vision. Our motivation is to try to find simple and efficient multi-object tracking solution for maritime computer vision. Our solution finally hit second place on maritime boating tracking challenge and third place on UAV-based maritime object tracking challenge. Our solution is based on tracking by detection paradigm. Object bounding boxes are detected in each image by a detector. A RID model extracts feature from bounding box. Then tracking process the data association to match object ID in the image sequence. For object detection, we used CBNetV2 architecture, which group multi-identity backbone and integrates the high and low level feature of the multi-backbone network, and gradually expand the receptive field to more efficiently performance object detection. For this competition, we use swing transformer backbone with FPN net and HTC detection head. For tracking, we apply byte track, which track by associating every detection bounding box instead of only high score 1. We combine the tracking feature from the previous frame with the detection score, which weight sum. The similarity distance for all bounding box is based on RAID distance. The remained high score detection box will keep as a tentative box until it appears again in the consecutive frame. For the lost unclosed box, the tracklet will be kept more than 10 frames in case of they will appear again. RAID and the RAID module, we leverage the MaCVi tool, which pre-trained on ImageNet 1K as our re-identification model. And this is our solution final result on 2MLT challenge. That's all. Thank you for listening.
Right. And finally, we'll go to the third place of USV-based object tracking, which is DLR boat track. I think Angel Bueno, are you here?
Hello, yes, I'm here.
Perfect.
I'm gonna get and share my screen. Okay. Okay, the screens and everything is everybody can see?
Yes.
Yeah, good. Okay, thank you. Yeah, I'm Angel Bueno, and I'm gonna present this the USB object tracking challenge or solution based on the SCAT YOLO and BOT sort that help us to achieve the third position in the challenge. I'm presenting in behalf of the team. We come from the Institute of the Protection of Maritime Infrastructure, which is sit in Bremerhaven. This is part of the German Aerospace Centers, and it's a small institute that has been recently founded and that features two main departments. One is resilience of maritime system, and our department, which is the maritime security and technology, specifically the data analysis and maritime situational awareness. In this regard, we followed all the specifications given in the challenge, and then we selected the tracking by object detection. We basically focus our object detector and we train only on the large data set that was provided on the MaCVi challenge. And of course, we use the SCAT YOLO V8 with C-band and extra prediction head, which has been very recently introduced by my colleague Borja, and that I encourage to see the presentation that he will give later, which help us also to achieve the third position in another of the challenge. As a data augmentation technique, we use the slice-aided hyperinference method, or SAHI, and then we slice all the images into 640 by 640s with 20% overlap. Then the tracker, we use BOT sort without the re-identification module, and then we tweak a bit the confidence threshold by looking at the statistic detector and confidence, and we basically, for the video 366, we use a high score threshold of 0.2, and then a threshold of 0.4 for new tracks and threshold of 0.5 for confirming tracks. And then for the rest of the video, we maintain the default parameters or close to BOT sort, but we reduce by 0.1. And that basically means that we obtain a high score threshold of 0.5, a threshold of 0.6 for new tracks and 0.7 for confirming tracks. Then here we can see that during inference time, we omit the slices, the SAHI method. We also perform interpolation on top, and then we attain the following the standard challenge metric with a HOTA of 0.193 and an IFD1 of 0.2.2 and a MOTA of 0.057. As the main key challenge that we saw is like we see that at least for the configuration and experimental setup that we have is that the small objects are hard to track, especially close range buoys, long range distance ships, and everything is something that it gives a lot of error in the detector. And also, of course, I think it has been mentioned, the object occlusion is also a big problem, and therefore there is a huge room for improvement in this setup for us. And as a summary, we just resort at tracking by object detection, in which our object detector is based on a SCAD YOLO with the attention component and the extra prediction head. And then the tracker is BOT sort without the re-identification component with attaining a HOTA of 0.193. And yeah, that's helped us to achieve the third position of the USB tracking challenge. Yep, thanks.
All right, thanks, Angel. Are there any questions from the audience? Otherwise, I'll ask a similar question as before. You said you used only Lars. Did you try using Coco, like a big number of boats, essentially? Yeah.
We tried to see if we can push it towards the Coco, but then we saw like we were really time constrained on this. So therefore, we focus a lot on performing the object detector really well, and I think Borja will talk later about it. And also, to basically make it also working with the SAHI and see whether on this low regime data set with the SAHI and everything can make it work. But yeah, there is a huge room from improvement from here. It's like as long as you can start using like SAHI with also the Coco and everything, it will like get much better for sure.
All right, thanks, Angelo, again.
Yep. Welcome.
All right, then we'll go to the first place of USV-based obstacle segmentation. I think Luca Zeta.
Yeah, can you hear me?
Yes, we can hear you.
Okay. So wait a minute, I'll start presenting. So do you see that?
Yes.
Okay. So hi everyone, I'm Luca Zeta, a first year PhD student from the Department of Mathematics and Computer Science of the University of Cagliari. And today I'm presenting Swim Squared. First of all, I'd like to start the presentation with a bit of constraint that brought us to this kind of solution. Well, first of all, the first primary constraint is time. So we are playing a challenge, so we do not have a lot of time for experiments to try very different things. And another key constraint is the resources. So all the models that we trained are based on MaCVi RTX 3060. So we have only 12 gigabytes of RAM, so we cannot try big models. So we cannot try a lot of things. So what brought us to this constraint is that we cannot train larger model. We cannot do a lot of experiments. So our approach must be focused in one shot. Well, in order to get a solution fast, we must think our model train. So we often think about transfer learning. So my study is primarily on plasma images, in particular malaria parasite. So for you, I don't think it would be interesting thinking about malaria and maritime environment. But if you look at the image, you can see that when you are working with malaria parasite, you are working with small details. Well, if you do that for small images, you can understand that in our study that the object dimension really matter. So if we transpose this kind of knowledge to last images, we have a lot of images that have tiny details, tiny objects. For instance, here we have, I think, the sand from some kind of structure, and we have the boats that have thin objects. So we leverage the background studies on malaria to Lars. So we invest our resources not in bigger models that can understand like some patterns in comparison to smaller models, but we invest into higher resolution compared to size. So we also perform color augmentation and moderate geometrical augmentation, because when you are working with strong geometrical augmentation, you can distort the small lines, small objects. So as for the model selection, as you already know, we use the mask deformer, our baseline. So basically, we watched that as the study for the mask deformer, the best results are obtained by transformers, by swing transformers. So we selected the largest model that we can fit in our GPU, but we also need to select a dataset that can represent in some way maritime environments. And I think that no dataset can represent that very well, but the cityscape dataset is composed by also some kind of objects that are elongated, that are thin, so we can try to leverage this kind of knowledge for the last dataset. So we increase the input size to 768 by 1536. We use the largest model that we can fit, is the swim based, and we, in order to fit in on our free RAM, we selected a batch size of 1. And as for the conclusion, you can see that by increasing the input size, we can very well see some kind of results that I think they cannot be represented by small images for this kind of branch and the says and so on. Thank you for your attention.
All right, thanks, Luca, especially for the last slide. Are there any questions from the audience? All right. If not, seems not, then thanks again, Luca, for the very nice question. And we'll move to the second place of USB-based obstacle segmentation from Tuan An Vu. Are you here?
Yeah, I'm here.
Oh, perfect.
Yeah, can you see my slide?
Yes.
So hello everybody. Today I will present our work, Transmari, transformer-based maritime obstacle segmentation. My group is SKUSD VGD group. So which include 5 people, Vũ Tuấn Anh, Nguyễn Trường Hải, Hà Tấn Sang, Phạm Quang Dũng, and our supervisor, Sakit Yang. First, I will talk a bit about the challenge on large datasets. So we face with 2 main challenges. The first one is low light image. As you can see from the picture, we cannot see directly which is the object in the image. It's so in the 2 red band box. So it will make our model hard to determine the foreground, background objects. Secondly, it's the reflection. So it's the obstacle based on the maritime. So there are many glass on the water, and so the reflection is also the main challenge because we cannot determine which one is the real and which one is the fake reflect image. So this one we propose to you 2 approach. The first approach named TransQ. This transformer-based architecture to enhance the performance of semantic transparent object segmentation. This is our work focus on transparent object segmentation like glass or door or something like that. So we utilize 2 transparent queue. The first one is boundary queue and the second one is reflection queue. It helps us to distinguish the transparent and non-transparent objects. Denote that large datasets has 3 classes with water. So it has reflection queue. And also we still need the boundary queue to separate different objects. So we aim to use TransQ for training the large datasets. As a result, our method is really lightweight and achieves really good MLU around 96.2. However, on other metrics like F1 score and Q score are not good because large datasets focus more on small objects and dynamic objects. And this type of objects did not utilize the reflection module well. So it makes our model mix a lot of objects and lead to the low F1 score. So to solve this problem, we propose to use our second approach, which is transmemory. This is the model by our smart transformer. So this is the pipeline of our model. So we will fit the image into a strong data augmentation method, would include color jittering, adding noise, and some image transformation. After that, we go through a math transformers. Note that math transformer is a high resolution transformer based method, and it can work well with this type of it can work well with small and also dynamic objects. We use SwinL backbone with ImageNet 22K at pre-training model, and the training resolution around 510 times 510. So to achieve better performance, I think we can just increase the training resolution to achieve it. So in summary, the advantage of it approach is that for the chain skill, it will work well with water-related class, with big and static objects. For transmemory, it will work well with small and dynamic objects. So we leverage the two advantages of both transskill and transmemory by pixel-wide ensemble between the two approaches. And finally, we obtain the result in the second place, around 77.8 Q score and 97.1 MLU score. So here is some visualization on the paper. Yeah, this is the end of my presentation. Thank you.
All right, thank you, Truong. Any questions from the audience? All right, doesn't seem like. Thanks again, Truong.
Yeah.
And we'll head to the first place of embedded USV-based optical segmentation. I don't think we have a third place for the one before. Sorry, it was that. So, we just have the, sorry, no, we didn't have that. Okay, so first place of embedded USV-based optical segmentation are from Nguyen. I think we'll play a video for this one. That, correct me if I'm wrong, Loise, but yeah.
Hi everyone, my name is Things. In this presentation, I will introduce the solution for the USB-based embedded obstacle segmentation challenge. This solution actually first placed on the leaderboard. The solution is based on eWater, a lightweight and efficient network for semantic segmentation. Its architecture includes report, backbone, decoders, and segmentation hits. I made some changes for the backbones. The original baseband freshness 18 is replaced by larger version freshness 50, which the new baseband feature needed for the decoder must be changed. Specialist features replay a 10, 19, 31st, and 49 are used because these output features have the same size as output from player 6, 10, 14, and 18 of freshness 18 baseband. For the experiments, the official shortcut of was used for training and exporting the model. The models were trained for 100 epochs with baseline 6. I only used the provided datasets for training. Images are resized to 384 by 768 for training. Now let's move to the results. The first is the impact of longer trainings. It can be seen that longer trainings improves the model performance. The original equation model with freshness 18 basebands achieves 41.6 in quality metrics with only 25 epochs of training. The score increased to 46.6 and 47.1 with 50 and 100 epochs of training. The next result is the impact of the backbone. We can see that larger backbones enhance the result. With 100 epoch of training, model with freshness 50 backbones obtain the best result with 54.1 Q, while model with freshness 34 backbone is slightly worse with 52.8 Q. Although using large backbone reduce in the inference speed. In this case, it is very work well because the result is still good compared to the required threshold, which is 30 fps. The final is the impact of augmentation. For most of submissions, I resize the training image by first resize it to make longest time not exceed 768, then center up. Lately, I use normal resize transform to resize and training image to 384 by 768. That leads to an improved score, which is the final score of my team for the challenge. Thank you for watching.
Thanks to the authors for that video. And we'll go to the second place of the USV embedded obstacle detection.
Hello everyone, I'm very happy to give this presentation. Next, I want to introduce the model we use to participate in this competition. MaCVi Mobile SegmentNet, a lightweight semantic segmentation model for maritime obstacle detection network. The model is an encoder-decoder structure. Let's take a look at the structural diagram of this model. In the decoder part, the size of the input image is fixed and the output size is 320 multiply 320 multiply 64. Then is sent to the decoder part after ASPP and concat operations. The output will go through to CBR models, and finally it will be converted into a 3-channel image through a convolution and linear difference operation. Finally, the predicted probability of each pixel is output through the activation function. Next, I want to talk about the case path of the model. Firstly, MobileNet V2 is a novel mobile architecture that significantly improves the performance of mobile models on various tasks and model sizes. It introduces an inverted residual structure and lightweight deep-device convolutions to enhance model representation capacity and reduce computational complexity. This approach emphasizes the importance of removing nonlinearities in narrow layers and copying the input or output domain from the expansive power of transformations. These two pictures display MobileNet bottleneck. Secondly, the ASPP decoding head consists of two main components, the ASPP model and the CBR model. The ASPP model incorporates the idea of special pyramid pooling, but with a different implementation. It employs interest convolutions with different interest rates to achieve multi-scale context representation. It consists of 1 multiply 1 convolution and 3 multiply 3 convolutions. It corresponding to a different interest rate, 3, 6, and 12. The ASPP model performance will due to its ability to perceive multi-scale information through interest convolutions. Additionally, the operations in SPP are parallel, allowing the fields of results from multiple interest convolutions to capture feature representations at different scales and better extract semantic features from the image. Thirdly, the other model is the CBR model, which consists of a set of convolutions, batch normalization, and reload activation function. These two images are displaying the interest convolution structure. Okay, I want to talk about my thoughts. To reduce computational costs and enable deployment on embedded devices, we utilize a lightweight backbone network, MobileNet V2, which is consistent with the approach adopted in the EWSR. Substituting a more lightweight backbone network effectively addresses the computational cost issue. However, this may have a negative impact on detection performance, and a balance needs to be struck between detection performance and real-time precision when constructing a segmentation network. Additionally, we believe that it is necessary to design a encoder path that corresponds to the decoder path, rather than simply replacing the backbone network directly, as this may result in suboptimal generalization capability of the model in the process of designing the corresponding encoder. Consideration can be given to matrix decomposition of convolutional kernel matrix and the adoption of the dynamic shift approach for activation functions. This is my summary of the approach.
All right, thank you for the authors for that video. And we'll go to the last two videos, which is USV-based obstacle detection, first place.
Hello everyone, my name is Mate. I'm a master's student from the Faculty of Electrical Engineering and Computing in Zagreb, and my colleague Magdalena and I are the winners of the USV Obstacle Detection Challenge. I will go over why we participated in the challenge, what tools we used, what datasets we decided to train a neural network on, and finally I will go over the results. We decided it would be a good idea to participate in the challenge because we have recently started work on a new project called Smart Blue Tourism, which deals with the problem of implementing new technologies in marinas and small ports. We are cooperating with the Marine Center of Excellence located in the coastal town of Rijeka, as well as some other companies. There are many smaller goals planned for the project, one of which is the development of a situational awareness module that would help boat skippers navigate in crowded areas, and it should also provide the general information about the port. The awareness would be achieved with LiDAR for close-range localization and regular or thermal cameras when the range of the LiDAR is not enough, and also radar and automatic identification system, which are used currently on boats and ships. Let's quickly take a look at the tools that we used for this challenge. For the challenge, we used 51, an open source tool used for creating datasets, seen in the next slide, and we also used the Ultralytics YOLO, You Only Look Once framework, to train our detection model. So 51 proved to be a useful tool for managing large datasets like the one needed to train our detection model for this challenge. Let's take a look at the 5 datasets that we used to train our neural network on. The first dataset that we used is the Google's Open Images version 7 dataset, filtered for only images that have boats in them. It is a large dataset with around 25,000 images, and it has close to 50,000 instances of a boat. The next dataset we used was the popular Coco dataset, again filtered for images of boats only. There are around 3,000 images in total showing boats, but we manually curated the dataset to around 2,000 images that have a bit more than 2,000 instances of boats in them. We also scraped the web for relevant images, not only of boats, but also other objects that can be found on the surface of water, like buoys or animals, and labeled the images ourselves. We ended up using 6 different object classes. We also use a dataset that we have taken by a static CCTV camera overlooking a busy bay entrance in Šibenik, a coastal town in Croatia. The boats were labeled by the type of the vessel they are, so there were 9 classes of vessels in total. And finally, we used the large dataset provided by the hosts of the challenge. It is a diverse dataset, and the labels are not only of different objects on the water surface, but also of bigger regions on an image, for example, static obstacles, water, or sky. We decided to use the YOLO architecture because we had previous experience working with it, and we wanted to test out the newest 8th version of it. Ultralytics claim that it is faster and more accurate than its predecessors, and seeing how the processing time was not scored for the challenge, we of course used the most complex model. As far as training is concerned, we trained on one dataset until convergence before moving on to the next. Training was finished on the challenge dataset. Now, these are the results of detection for the static CCTV camera. The green box represents the detection. Here's another example. This is a video taken from shore. The model struggles with the boats in the distance that have their lights turned on because it is hard to find nighttime, sunrise, or sundown images of boats online. Thank you for the attention, and thank you for allowing us to present our work at this conference.
All right, thank you for the authors of that video. So the last video now.
My name is Andreas Michel. I'm working for the Fraunhofer Institute in Germany, and I will present our solution to the obstacle detection challenge. On this slide, you can see the framework, the model, and the data sets. The framework we used is Detection, and I think it's a very common framework, so I don't think any introduction is necessary. Model, we use the co-editor algorithm. It's a very new model, and we use it in combination with a Swin large backbone. Datasets, we use the last dataset as expected, and in addition we use the Objects 365 dataset and the MS-COCO dataset. Co-editor is a detection transformer, and as you can see here in the image, detection transformer has a much more simpler architecture than traditional architectures like YOLO or faster RCN. There's no RPN, there's no non-maximum suppression. And yeah, so here on this image you can see the concept of it. You have a backbone, it's producing embeddings which are tokenized and then encoded with positional information put in a transformer. It's here a full transformer, encoder and decoder, and the output of the transformer is fed into the prediction heads. Detection transformers are usually trained with a bipartite matching loss. This means every prediction is mapped to one ground truth, and this works, but it's not very efficient. And co-editor tries to improve this aspect. And the basic idea is to use auxiliary heads, so we don't have a one-to-one set matching, but a one-to-many label assignment, and this leads to better trainings efficiency and to a better performance. Here on this slide you can see the quantitative results of our approach. We used always co-editor with in Swin large vision transformer. We use test time augmentation in form of multi-scale augmentation and flipping of the image. We use additional data, and the training stages here are an important factor, because here if we only used one training stage, we trained it from scratch only on the last obstacle detection dataset. If here is a 2, it means we trained it on, we use pre-trained weights from the, Objects 365 and MS-COCO, and when trained in a second stage, only on the last obstacle detection. And with 3 stages, we have a middle step here and trained it on images from MS-COCO, which are containing a ship, in combination with the last dataset with all objects. And yeah, fine-tuned it when only on the obstacle large detection dataset. As you can see, if we don't use any additional data or so and no test time augmentation, we get the worst result. Makes sense, co-editor is a very large algorithm, and it needs lots of data to function well. If we train this in 3 stages and apply test time augmentation, this was kind of wondering for us, we had a decrease in the F1 score in comparison to the solution without test time augmentation. And yeah, at last you can see that the training in 3 stages led to a performance boost. And yeah, so on this slide you can see the qualitative results. We picked 2 scenes, one with a sailboat, one with multiple motorboats. Yeah, I hope the results are sufficient. And thank you for your attention.
All right, thanks for the authors also for this video. And now we move to the last presentation of the competitions, the 3rd place of the USV-based obstacle detection. I think you are online, Boya.
Yes, I'm here. I hope you can hear me well.
Yes,
Okay.
perfect.
I'm sharing my screen. Hopefully you can see it now.
Yes.
Okay, yeah, so then on behalf of my team, also I will present our third position in the USB-based obstacle detection challenge, for which we used what my colleague has already introduced a little bit, the SCAD YOLO V8 architecture plus CBAM. And yeah, I also work in the same team as him in the German Aerospace Center. So first, a little bit of introduction, what the modification of YOLO V8 means. So we added in previous works, the 2D scattering transform and the CBAM module. In regard to the 2D scattering transform, it was proved in previous works that is key in signal processing and useful for image classification. Specifically when the input image is convoluted with different orientations of a wavelet. This highlights different frequencies present in the image. This transformation also has translation invariance and stability to deformations. And also it leverages the robust discriminative features provided in the input image. Then we proved in previous works that combined with the convolutional block attention module, or CBAM, it produces an increased feature representation of ships and feature maps of the ships. So then we took these two modifications that we used in the past. So for this, we applied this to the YOLO V8 architecture. What we did was to add the scat block that contains the scattering transform at the beginning of the backbone of YOLO V8, and then we added the CBAM module in the prediction heads. This architecture, we already proved that it works for ship segmentation in a different data set that was used for maritime awareness. So we decided to give it a shot for the challenge as well. In this case, we also added an extra prediction head in the architecture, and we also used the slice-dated hyperinference, or SAHI, for both data augmentation and for a better performance during inference. So regarding the results using this architecture, so we generated an augmented version of the large data set using SAHI. So we created splits of every image of 640 pixels by 640 pixels with 20% overlap. Then we picked the largest YOLO V8X, and then we applied our modifications with the scattering transform and the CBAM module. And we train only in this augmented version of LARS for 40 epochs using an NVIDIA 800 GPU. Then in the inference, we also use SAHI, as I commented before, and we achieve 4 FPS. And the F1 score achieved by our method on the test set for the challenge is 39.79. And here is an example of a prediction on the large dataset. Yeah, so to sum up, we made use of this architecture, SCAD YOLO V8 and CBAM as object detector. We train on the augmented LARS and also use SAHI. Our F1 score was 39.79. And this led us to the third position of the challenge. And that's it from my side. Thank you.
All right, thanks, Boya. Are there any questions? Zoom or in person? All right. No questions? Okay, thanks again to all the authors or to all the participants of the competitions. We're gonna have a short break of around 10 to 15 minutes. And yeah, feel free to meet up virtually in Zoom. I'll leave it open here. And yeah, see you soon. All right. I hope you can hear me still on Zoom. Perfect. Thanks. Yeah. Okay, so after the short break, we'll go to the very interesting now a keynote. So the next keynote will be from Danilo Petrocelli. He is a senior machine learning engineer at Maritime Robotics, and he will talk about the machine learning and deep learning challenges for autonomous maritime robotics, for USVs and UAVs. So Danilo, are you here?
Yes, hello Benjamin.
Hi,
Can
Danilo.
you hear me?
Yes, we can hear you. Perfect.
Perfect. Thank you for a nice introduction. So I will try now to share my screen for the presentation.
Yeah.
But I think that you have to, okay, give me the right for perfect. Can you see my presentation?
No, probably you have to switch the application that you're sharing.
Oh, okay.
Now we can see it.
Perfect. Let me just go in presentation mode. Perfect. Okay. Hopefully you can now see the presentation.
Yes. Perfect.
Perfect. So the way I structure this presentation is just introduce about like maritime robotics platform, and then discuss a bit use cases, operations, technology, and finally R&D projects. But firstly, let me introduce like maritime robotics. We are leading provider of autonomous navigation systems and uncrewed platforms. We are based in Trondheim, Norway, And we are like 65 employees. We are still growing as a company. And our main markets are mapping, survey, environmental monitoring, scientific, and defense and security. As I said, we are enabling and we manufacture like uncrewed aerial system, autonomous surface vehicles, and also what we called autonomy on board. Basically, it's autonomous kit for converting any vessels of customer choice from manned to unmanned, or even better, autonomous. So talking about maritime robotics platforms, we prototyping and also manufacturing like the fixed wing Folk for the UAVs. And also we use like some multicopter with custom design payload for UAVs applications. The Falk is a fixed wing and has a flight time of 2 hours and a wingspan of 3 meters and 40 centimeters, and also an operation ceiling of 6,000 meters. And it can be equipped with plenty of sensors and custom payload as well. With regards to the USV ranges, our products depends from the use case. For example, for sheltered waters, we do have like the Otter and the Otter X, respectively 2 meters and 4 meters and a half. And also for coastal and open waters, we have like a huge vessel called Mariner that is 6 meter, and the Mariner X that is 9 meter. The Otter, those are some specification for the Otter. It's the smallest USV of our platforms. It has like 20 hours of battery with a payload as well, depending also, of course, of the payload, and it has a length of 2 meters, more or less. And this slide is very, let's say, it's very peculiar from the modularity of the Otter. It gives like the idea of how modular the Otter is. Basically, you can disassemble and put like in a small van and even in a station wagon, and then be ready for the next survey. You can literally not do it the same with the Mariner because it has like different weight and also different length. And of course, it can be used like for a different kind of scenario, like in open waters as well. Same discussion for the Mariner X. It has been built for survey, not for speed. And it's like a large deck on the back to for like different kind of sensor payload, and it can be equipped also with taking and land off platforms for fixed wing and multicopter as well. And here is a clip of of how important it is to go unmanned and autonomous in terms of survey. Okay, this take a bit like the idea of how to do like vessel like in autonomous mode or in manned vehicles, because something like this can happen like especially in the Arctic. So in terms of use case and operations, I would like to introduce some collaborative surveys in terms of use cases. But first, why we do have like collaborative surveys? So basically, what is like the kind of motivation for doing collaborative surveys? So marine survey operations are cost and time expensive, and still today are mostly performed by a single large vessel and are highly daily operating costs. So basically, employing multiple USV can and will increase efficiency in doing the survey by running, for example, group formation of USVs, and also will be more efficient in terms of data gathering. And this will result in a cost and time efficient surveys. Of course, there are like several different kind of settings in terms of collaborative surveys, for example, using multiple USVs, like the Otters, for example. And I do have like a very small clip on this. In the clip, I just showed you like 2 Otters that are following information mode and other unmanned vehicles. And of course, there are also several different settings to use, like, for example, USV and autonomous underwater vehicles. And again, the same principle is like to use modular multi-vehicle system, for example, for seabed surveys. And the result, for example, would be like to planning and control coordination, and also to have like a low operator footprint. And you can just combine like the eye position accuracy by the Otter, the USV in general, and the high resolution sonar data acquisition by the IUV. In terms of unmanned surface vehicles and UAVs, it's still possible that we do have like plenty of tests going on at Maritime Robotics. For example, when we employ like a USV for doing the bathymetry of the surveyed area, but at the same time, we also collect information about the orthomosaic mapping of the same area and the 3D model itself. And we are doing like more tests on this with a new platform, the Mariner X, because as mentioned before, the Mariner X is equipped with a takeoff and landing platform. And this is quite useful when we are doing collaborative survey like this in both like cases with fixed wings and with multicopter as well. In terms of technology, I will like just give you an overview of the main technology at Maritime Robotics. So basically we do have like the principal component is Vehicle Control Station, VCS, and OBS software onboard system. So basically in VCS, it's everything that it can be monitor sensor and payload data, as well as plan autonomous survey missions, while on OBS there is like the control algorithm and the sensor interfaces. And of course, the operator has like different kind of operation modes, for example, manual remote control, and there is also a feature for waypoint tracking, station keeping, formation mode, and so on. And then our goal is to provide supervised autonomy and to provide operators with situation awareness system in order for them to have like insights from data in real time, and also to have every time like an overview of the surrounding of the vessel. And this is important because then the operator can intervene in terms of if there is something that is not quite right, and they have always like an 80 degrees 360 degrees, 180 from the front and 180 on the back to have like everything under control. Then of course our goal is to do like autonomy-based suggestion to the operator based on the object detection and tracking, and also to provide route alternatives, and also to have like sensor fusion-based aiding system with plenty of different sensors all together. And here you can see like a real-time object detector running on the infrared cameras from the Otter. It has been one of the first test trial field tests in this direction, and of course since then we are expanding our system towards like multiple cameras that are using like both infrared and electro-optical cameras. with deep learning enhanced system as well. As I said, our product in terms of enhanced situation awareness and collision avoidance is called Seasight. And we do have like different kind of settings for this product. Basically, this version is for the Otter, and it comes in 3 different versions. One is only camera with 4 cameras, 180 degrees from the front and from the back. One also with LiDAR, and it can be combined with LiDAR cameras altogether. And as I say, the function of this product is to visualize, detect, and avoid. So basically, it's kind of situational sensors for the operator, for the remote operator. And this is a short clip of now the system it works, also to avoid obstacle and to have like an active collision avoidance system. And you can see that with the LiDAR, we have information about the obstacle. And in this case, like the Otter and the Seasight is activated, and then the system can be reroute the original pipe to the obstacle automatically. Then I can give you like an overview about the system of the Seasight system. So basically, as I say, it depends from the configuration. There are like several sensors and workflows. For example, from the camera, the video stream workflow is based on the bundler, video stabilization, and stitching. On the LiDAR, again, there is like the IS, radar, and LiDAR sensor. There is like association, feature extraction, and fusion. And then there is like the machine learning module that is like this inference engine that will overlay all the results with the video stream, and will give you like an output, the video that I show like in 2 seconds, in 2 slides. Now the next slide is like on the machine learning module itself. For us, it has been important, like both the data infrastructure and the machine learning infrastructure in terms of model development and model optimization as well. And as you already know, for us, it has been very important to have these like built-in workflows. So the first one is for ingesting the data. So it's the data infrastructure itself. And then the second one is more related to the model development. And the third one is the optimization of the model that runs on the embedded device with the usual suspects of tools and stacks like DVC, CVAT, ONNX, and of course, NVIDIA TensorRT. As I said before, all this system gives like this kind of output, and there is like a video that shows the kind of output that we are having from this kind of system. As you can see, there are like information overlaid on the stitching of the cameras together with information about the IS system, with the obstacles that are actually in line with the Seasight and with the cameras. So you can see like the range from the cameras to the actual object, in this case vessels, and all the information displayed there, like for example, the meters, the specific like property of the vessels, and so on, that comes from the IS system. We are also switching from a semantic segmentation model in order to have also region no-go, go, and no-go zones with state-of-the-art semantic segmentation model. And finally, R&D projects. So I will give you like just a brief overview about 2 projects that involves like UAVs and deep learning or anomaly detection, and other 2 R&D projects, actually other 3 R&D projects that involves like both AI developments with more cooperative surveys. So the first one is called OceanEye Next Generation, and it has as a goal improving like the route visibility for huge vessels. And to do so, we designed like this software system that can detect, classify georeference, and report back to the operator objects that are not supposed to be on the sea level. And also, we designed and prototype a camera rig system to be switched between fixed wings, and also a multicopter. And we did so with our partnership with PGS, SINTEF, NTNU, and Norse. As I said, we do have like this kind of design and manufacture camera rig, and we started with 3 infrared cameras and 2 electro-optical one, and then downscale the whole system for a specific application to 1 electro-optical and 1 infrared cameras. And the payload, as mentioned before, can be installed both on the multicopter and on the fixed wing called Falk that I mentioned earlier. Those are some really early prototype of the system. And we did test this system also in another project called Digital Arctic Shipping. That was particularly interesting because it was like an expedition through Greenland for 22 days in very harsh environment. And we with the goal to actually deploy a real-time deep learning-based system for ice monitoring and sea ice classification. And those are some of the harsh environments that I was referring earlier. And we actually, as a part of the project, we collected plenty of images from both cameras, infrared and electro-optical. And we also collect those and create orthomosaics, geotagged orthomosaics, and 3D models of icebergs and ice stations that were very important to the scientists. And during the journey, we also had the chance to meet some clumsy friends. Those are some of the landscape that we acquired during the journey. And as an R&D project that has to do with collaborative surveys, I would like to introduce COMAP. That is our like specific goal to develop an end-to-end solution for bathymetric mapping with UVs. And as to go, we have developed this with OceanScan Marine System and Technology and the University of Porto. And also the Atom project is a first-of-a-kind system to actually deploy and recover underwater platforms with a collaborative platforms USV plus unmanned underwater vehicle. That actually the payload of the UAV vehicles will be like an underwater hyperspectral imager developed by SCARF Technologies and Ecotone. And also the Sirius project that has like been developed with ESA and EOMAP that has like the object of increase the coverage of surveyed areas by usage of EOMAP satellite derived information and in situ data from USVs like the Otter. So as conclusion and future developments, I would like to leave you with this slide in particular. I believe it is a summary of what the future will look like in terms of machine learning and deep learning applications. And as I mentioned earlier, at Maritime Robotics, we are using machine learning and deep learning mostly for situational awareness. And we will continue to optimize the current solution, at the same time deliver like top-notch products and adding new features to the current products to assist our customers and the remote operator with their daily working tasks. However, we would like also to contribute more and pushing our limits on developing machine learning and deep learning contribution to other fields in the maritime scenario. As the AI landscape is evolving very quickly in our field, we really believe that the key to succeed in this is engaging with new collaboration for both R&D and also for product developments. In this way, we can successfully apply deep learning to solve challenging problems, like, for example, seabed classification, scoring, and cable monitoring, and learn a lot during the whole process, with the final goal to make operator and, in general, experts' life way easier. So thank you for your attention, and if you have like any question, please feel free to let me know.
All right, thanks, Danilo, for the very visual talk. I think it gave a really nice overview over what you guys do at Maritime Robotics. Is there any question from the Zoom audience? You are hardly audible, Georgios. We can hear you a little bit, but it's very muffled.
Okay, just give me a second, please. Let me see if I can increase the volume for my Zoom call.
I think it's better now.
Yeah,
Maybe we
now
can
it's
understand
better.
you.
Yeah.
It's better? Okay. Thank you, Danilo, for this very nice presentation. It was really informative. I would like to ask you a question. Now is better? Now? I found it's okay. My question was when you showed the inputs of the different sensors, radar, LiDAR, optical, etc. From what I understood, they are all used for the machine learning methods that will be used for the situational awareness. Are they used simultaneously during the training? Or are they used to train separate models in order to be more adaptable to different things that are to be detected or for to use for the marine robotic system?
Thanks, Georgios, for your question. Actually, the future is our goal for the future is to fuse all together and build like the machine learning module on top of each of the sensors. For now, the first prototype of the system will be used like just for computer vision related input. So the camera and the LiDAR in some of the tests that we did actually. But yeah, for the future, we already started like this journey. Would be the goal would be like to use like every input of the sensor for building like the machine learning module in order to combine all together.
Okay, I see. Because my main, let's say, question was due to the different nature of the inputs, one would expect that if somebody wants to simultaneously train data that come from optical inputs or LiDAR inputs, would have to make some sort of pre-processing to make them bring more joint information during the training. So from what I understand, this will have to be one of the issues that will have to be tackled. So yeah, that was
Absolutely. This, and if I can add also the synchronization between different sensors, that sometimes it's something not so easier, at least when you're using like multiple sensor, multiple cameras, and perhaps multiple LiDARs as well.
Yes, absolutely. Thank you very much, Danilo.
Thank you.
All right, just maybe two small questions with regards to your data that you're using for your object detection and tracking. I guess you have your proprietary data sets, but can you comment a little bit on how you generate these data sets and like how big they are, if you can?
Yes, absolutely. So basically, we do have like different platforms, as I said, and we use our platforms to collect data. And this is it's also something that we do more often in collaboration with NTNU. So basically in collaboration with students, so that they can, for example, starting the bachelor, the master degrees, and starting like help us in collecting more data and building new data sets. So for now, we're using our dataset and some of the open dataset out there, but mostly like collect the dataset in Norway. And the idea there will be like to somehow expanding and use like our customers' dataset, and again do like some specific operation for collecting data specific like in some part of Norway or in some part of the world as well. But of course, as I said, we do believe like a lot in collaboration. So, and I really enjoy like your work in terms of dataset as well. So that will be totally possible to collaborate in terms of dataset creation. In terms of dataset size, so far the system that I showed you has been trained like on more or less 20,000 images, but we are still working on the dataset creation as well.
Okay, awesome. Thanks. Maybe one last question with regards to AIS. You mentioned shortly you use also AIS. How do you associate like AIS and the actual detections from RGB? Do you like, especially in the presence of a lot of movement, like do you use somewhat classical computer vision methods for like 2D to 3D projection, and or how is there some more sophisticated solution that you use?
We do have like a pipeline for stabilize everything before like using, for example, infuse the data with the IIS. But we do, I can see that I can say that we do use like some classical computer vision methods there before going like towards the IIS data.
Okay. All right, perfect. Right, if there are no other questions, then thanks again, Danilo, for your very visual talk. Thanks for staying up. I'm happy that it worked out with your flights, even though you said it might be critical, but all
Yeah,
worked out.
I still don't have my luggage with me, so they managed to to lose my luggage, but finally I'm here. So I'm very happy to be there. Thank you for having me.
All right, good luck with your luggage and thanks again. All
Thank you.
right. In that case, we'll go on to our last keynote. So let me introduce her. So it's Kakani Katya. She's a principal engineer at the Monterey Bay Aquarium Research Institute. And yeah, she's the lead of the institute, and she essentially deals with always for imaging in the deep sea for environmental studies, and she has been very famous with FathomNet. And yeah, I'm very excited to hear your talk on that. Kakani, you here?
Yes, it's nice of you to say that I'm famous, but I appreciate the invitation.
Awesome, yeah, perfect. Do you mind sharing your slides?
I will do that. Let's see. Just bear with me while I get things ready. So I believe you see the slides.
Yes, perfect.
Perfect. Yeah, so thank you for the invitation. I hope you all are enjoying Hawaii. I wish I could be there. And really wanted to take the opportunity to talk about a project that we've been working on for several years now. The last conversation about data sets and sharing really resonates, especially with this project called FathomNet. And then so what I want to do, though, is set the stage first, right, for the challenges that we face when we're talking about monitoring the oceans, particularly when we're trying to monitor ocean life. And there's a study by Aaron Satterthwaite and many others where this image or figure comes from. And what they did was they looked at observing programs around the globe, which systematically sampled marine animals in situ for periods longer than 5 years. And so each of those colors indicates the potential source for the kind of observational data that's required. And these are, these big data aggregators like OBIS and GBIF that are available internationally. And what they found was that about 7% of the ocean surface area was covered by long-term biological observations. So ocean surface, right? The ocean is a massive volume comprising 97% of the habitable volume on the planet. And there's also estimates that there's anywhere from 30 to 60% of life in the ocean that's unknown to science. So if you wanted to do a quick Google search for a lot of the animals in the ocean, you probably won't reveal any data, especially image data. And that it's already a big challenge to try and be able to identify known objects, never mind unknown objects. And so that's another computer vision challenge that the community needs to face. And so solving our sampling problems, right? So filling these observational gaps means that we have to move away from historical approaches like using research vessels and to solve our problems, we need to have major advancements in robotics and automation and especially in how do we process this biological data. And we're also in a race, right, to fill these knowledge gaps and observational capacities, since there's a number of activities looming in the horizon that exploit resources and conflict with biological communities. And there's this whole area called the blue economy, right? And these are industries and institutions that and activities that you look to utilize the ocean. Traditionally, it could be fishing or offshore oil and gas. More recently, there's a lot of interest in aquaculture, offshore wind, and more recently, deep sea mining. And so there's an increased need to understand the space in which their activities intersect. And to grow this blue economy requires understanding its impact on the ocean environment, particularly the lives that live there. And biological observations, there's many different ways that you could do this. One is environmental DNA, another is acoustics or sound data, and then, of course, imaging. And so these are all active areas for AI research. And what I'm going to talk about here, because we're at MaCVi, is at least imaging. And so in order to understand and characterize underwater environments, researchers collect image and video data to catalog the geologic features and life that lives there. And so visual data like this video, incredibly rich resource, right? It yields information about substrate type, animal species, abundance, relative distributions. All of these things are important quantities for measurement. And so the current approach is to have a visual taxonomic expert annotate this footage, and depending on the type of environment, can take anywhere from 3 to 5 times as long to process as the raw footage itself. And so this is not a scalable approach where institutions, labs, and individuals lack the resources and the expertise to process this information. And so although collecting visual data for monitoring marine life has increased, our capabilities to process this information has not. So far, US-based exploration organizations have collected more than 300,000 hours of underwater video, but less than 15% of that data has actually been processed. And we're also seeing an exponential increase in imaging volume as the blue economy grows. And so what that means is that we're just facing a deluge of visual data with no real solutions to rapidly process this information to monitor life in the ocean. And it shouldn't surprise anyone, right? The question of whether artificial intelligence can address this big data challenge. It's especially true when you see tantalizing footage like this one from a paper in 2020 that shows, how you can readily distinguish between objects like people, chairs, and other things. And these advancements have been furthered by establishing massive image databases containing millions of images that are scraped off the internet and are further enriched with information that's useful to the algorithms that are being used. And I just want to highlight 2 of these, databases, and it shouldn't surprise anyone here. ImageNet was published, or at least the original paper was in 2009. When I grabbed these statistics, this was probably over a year ago, more than 15,000 paper citations. And then another data set called Microsoft COCO, Common Objects and Contexts. And just the scale of these, ImageNet, it contains about 14 million images for 22,000 different object categories, whereas COCO has 330,000 images, but 1.5 million object instances across 80 object categories. So these are massive databases that are readily available, free to use, for you to be training algorithms, testing algorithms, etc. And if we think about what do we need for the ocean, particularly around biological observations, what does this mean? And what could a big data set allow us to do? And so one of the things I'd like to show is, my institution at MaCVi, we have a 30-year expertly annotated database full of video data that we've been collecting. And it's annotated by experts, and we've been able to augment that data so that you can have labels that can be used to train algorithms. And if you take the geolocation of all the labeled data that MaCVi, my institution, has, you can see that we're very, very limited geographically. Never mind that we're also limited by the different animal groups. I think about 1,500 species of animals is what the data are associated with. And so you can just see by mapping where our data is located, there's significant gaps inherent to our data set. And what we want is a labeled set that can be truly representative of life in the ocean. In order to do this, we need something more. And so what we need is a big global scale repository to aggregate representative imagery for all life in the ocean. Similarly, right, to the scales at which we see in the terrestrial space. And so that's why we established FathomNet. So FathomNet is a public underwater image database for labeled data so that the community can contribute their data and use it to train machine learning algorithms. FathomNet provides imagery and metadata for ocean life and includes additional concepts like equipment, debris, and other geological features. I want to say, though, that FathomNet is extensible. It's not only containing underwater imagery. If imagery contains a marine concept, it could be a live concept, a geologic feature, that data can be incorporated into FathomNet. So FathomNet was founded by MaCVi, C-Vision AI, and Ocean Discovery League, and currently contains visual data from a number of different sources, including NOAA's Office of Exploration and Research and National Geographic Society, with many other contributions. And our goal is to assemble about a large data set for 200,000 different animals that are currently identified in the World Registry of Marine Species. And we want to collect anywhere from 500 to 1,000 labeled images per species so that we can, classify and distinguish individual species in our observations. And so if you'd like to learn a little bit more about the database, we published a description of the database in Scientific Reports in 2022. And really what FathomNet is, it's what we're trying to do is push this idea of an open source ecosystem. This is something that I think, the terrestrial space has done a really great job with in terms of making sure data is accessible and freely available. And I think the marine science community has largely lagged behind, partly because, well, one, it's very, very expensive to acquire the image data that you need for your training. But then also there aren't or hasn't been very straightforward ways for you to share that or to aggregate that data. And so what FathomNet is and what we're trying to promote is an open source ecosystem and change the way in which we use and share data. So the database can be accessed via the website at fathomnet.org or via an API. If you go on the website, there's the ability to search the entire database, understanding the geographic references of the observations. You can also take a look at the imagery that's within the database. There's a lightweight annotation tool, so you can augment the data or correct the data that are in the database. And then we have created a bunch of tutorials, videos, shared code on our GitHub pages, as well as blog and YouTube. So what we're trying to do is lower the boundaries or the barriers to using this data, but also training models and applying them elsewhere. And related to training models, so what we've also set up is a collection of machine learning models that are found in the FathomNet Models Zoo on Hugging Face. And the reason why this is incredibly important, right, is that, if you have your own labeled data or you're using labeled data from FathomNet, The idea is that if you're training algorithms using that data, that you should really be sharing those algorithms broadly, because that can actually bootstrap the analysis process for someone else who might not have the access to the compute resources, et cetera. And so what we're trying to do is make these models readily available, and through the Hugging Face website, I think there's 5 or 6 different models now that can be freely used. And what we're also doing is really trying to build community around the database, which sounds really boring. But the idea here is that the database is serving a wide range of individuals. So it's not only serving, people who want labeled data, so the computer scientists, so the computer vision researchers. It's also a database that's serving the marine science or taxonomy communities, because it's a collaborative space where people can ID animals, compare individuals, perhaps also help with education and training of new taxonomists, marine scientists. And so what that means is that over time, we've been engaging with a really broad community of individuals. This includes experts in marine science, machine learning, and computer vision, but also to enthusiasts, so people who might not have a degree in marine science or computer science, but want to process and participate in processing visual data. So in this time, we've had almost 800 people register for our workshops, almost 10,000 publication downloads since we published that paper describing FathomNet. And so what that means, it's actually in the altmetrics score of 99th percentile of all journals tracked ever. Which again is surprising to me because it's a database paper. We have had more than 1,000 model downloads, 566 database contributors, and almost 6,000 independent website users representing 93 different countries. So, if the goal is global coverage of life in the ocean and, sharing of that information broadly, I can't say that we're there yet. I think we're on our way there yet, but the only way to solve this problem is to be very inclusive. And so as we've rolled out FathomNet, so FathomNet, we published that paper about 2 years ago. FathomNet went to V1, version 1, which has all these community features. Think of it as a social media network for taxonomists, marine scientists. So that was launched in July of last year. And what we've learned from talking with a lot of different groups and individuals is that labeled data actually isn't enough for the ocean science community. People who know how to use labeled data, right? It works for their applications, but most of the marine science community cannot actually download labeled data, train algorithms, apply them, and readily iterate on this processing pipeline until you have annotated data out. And so really the challenge is to create data pipelines where visual data comes in, undergoes an interactive process that involves human verification, AI training, AI predictions, and then repeat, right, until you have annotated data out. And labeled data like FathomNet, right, is used to train AI, but model performance is never perfect for the first time, so that requires human verification. And so you need human input. You need human input at multiple times in this process. And so the biggest bottleneck is actually human verification, not labeled data. And so how do you leverage human verification where you have a limited number of experts that have knowledge, of the species of animals that are found in the ocean, but a plethora of enthusiasts with more general expertise, that could be people who go to aquariums or like watching documentary films, etc. And so the way we decided to pursue this is through a collaborative research and development program called Ocean Vision AI. And so what the approach here is that we need human AI interfaces that engage a broader community of individuals that range from experts in marine science and computer vision and machine learning all the way to enthusiasts. And so in our design process, we learned that there's no one interface that can be used to address this broad community, and that instead we should be designing human AI interfaces that target each of these groups. So FathomNet actually targets experts in taxonomy, marine science, and machine learning, and provides a mechanism for these groups to contribute their expertise and knowledge in an efficient and effective way. And so again, and this is, I think, why that the potential value, right, for FathomNet is that it represents this global image, a machine learning model repository where, you know, it's publicly available, but really it serves as a taxonomic expertise aggregator. So, you know, scaling up our knowledge, our capacity, and sharing that widely on what it is, like what are the animals that we're looking at in this visual data. And I just wanted to add that we've entered an agreement with NOAA's National Center for Environmental Information. So that's their big data hub. And they've agreed to host data on FathomNet for up to 75 years from contributors all over the world. And so what we're working on right now is building these data ingest pipelines so that you can upload a zip file to FathomNet and it'll automatically, you know, take that data hosted on persistent URLs that are maintained at NOAA and then made broadly available through FathomNet. Another big thing that we've been really, really excited about and are excited about doing again this year is a FathomNet Kaggle competition. And we've been doing this in collaboration with the CVPR workshop, the fine-grained visual categorization workshop. So this last year, we had our first Kaggle competition on out-of-sample distribution. And then this next year, I actually don't know what we're going to do yet, but stay tuned for another opportunity. So here's in the middle, right, the activity called the portal enables researchers who collect ocean visual data to access state-of-the-art data pipelines to process their visual data. And the way this works, right, is really you're trying to provide access to ML data pipelines where you can upload, you know, make public or private repositories, select, train, deploy machine learning models, verify or augment the labels that you would get from this process. But most importantly, right, exporting annotations that you might have in getting it into the hands of the person who needs them. So that could be, you know, exporting annotations to FathomNet. So we're enriching FathomNet, or to these big data aggregators like OBIS, GBIF, right, making data fair and accessible. And then last but not least, what we've been focusing more recently on is like, how do you engage enthusiasts and have enthusiasts interact with underwater visual data and contribute to these data pipelines while also learning about ocean life as they go? And the approach that we've landed on is called Fathomverse. And so Fathomverse is a game. The tagline is exploring the final frontier on Earth. And it's an important collaborative effort between MaCVi and the Monterey Bay Aquarium and a number of other team members. The idea here is that we can have a really diverse audience, high school age and up, people that are ocean lovers, animal lovers, or armchair explorers that just have a general interest in animals and ocean facts. And what we're creating is a mobile phone app on iOS and Android. And we've been beta testing the app since this summer. And in over a 2-month-long period, we'd had almost 3,000 signups, more than 1,000 unique users or players, and generating more than 430,000 annotations. And so this is, we're in development for the first full version of the game, and it's looking like we will be launching that game as early as April of this year. And so if you'd like to check that out, you can go to fathomverse.game. But really, right, the idea here is to create a mechanism for us to engage a wide range of individuals, but also have these individuals contribute meaningfully to the human verification needs required to complete this iterative loop. And again, getting annotated data out. So FathomNet, this is where the experts live, not a lot of experts. The portal, these are people who have the visual data that have a need for processing this visual data. But then Fathomverse, these are people on their phones, you know, commuting, let's say, contributing labels so that all together we can solve this human verification problem. And so I just want to, I'm going to end pretty soon, but what I wanted to share with you are just a couple examples of some outcomes that we've had with using data in FathomNet, and also things that we're looking towards in the future. And one of the first things that we've already done here at MBARI is train up a number of algorithms for use within the MBARI video lab. So our video lab is a group of 6 to 7 researchers whose job it is to convert this pixel information into annotations. And we've been developing through our data pipelines here a variety of different user interfaces for people to interact with, model inference, but also correct them, and then retrain models, etc. So you can find some of the models that we've trained using this process in the FathomNet Model Zoo on Hugging Face. But I think really accepting that, conditions change, labeled data, distribution shifts are very real. And so it's going to be very, very hard for a very long time to have a model that is so robust in all these different conditions, like generalizes really well. And so what the focus then has become at MBARI, but also in this Ocean Vision AI project, is thinking about how do we use or utilize messy labels, and how do we also augment or improve them as quickly as possible. Another thing that we've been able to do as well is, using FathomNet and additional image data that we've been collecting using our autonomous systems or our remotely operated systems. We can train models, and we've also incorporated these models into vehicle controllers to not only track individual animals, but actually go out, search for, and then observe these animals for a long period of time. And so this is a demonstration from a few years ago. We actually published an early version of this algorithm, calling it animal tracking in MaCVi, I think 2 years ago. But on the top left, you can see the bright colored text that shows the mode that our vehicle is in. And we are specifically looking for a giant larvation. So the model is tuned for looking for an individual. And once that individual matches a class that we're searching for, then the vehicle behavior changes, and then we're able to do observations for a long period of time. And so it's algorithms like these that can really change the way we deploy vehicles to explore the deep sea, but also discover life and monitor it for a long period of time. And so I just wanted to say, that these data systems and data infrastructure, right, this open source approach is really, really important and could be very, very powerful. And so what we're hoping is that, other members of the community also agree and start contributing to and utilizing FathomNet. So with that, I'm happy to take any questions you might have.
All right, thanks, Kirkani, for the very nice talk to describe the initiative. I really like the initiative. I think it's a very important and very sustainable thing that you're doing, because oftentimes you see like just data that's being published and it's not really in a sustainable way. So I really liked it. Are there any questions from the audience in person or on Zoom? Otherwise, I'll start with some questions. Actually, I had a couple of questions, but your talk really nicely answered most of them. So I was going to ask something about competitions, but you have the CVPR competition. Is that the first competition of that kind? And more generally speaking, if you want to engage with a lot of people and want to form a community, have you thought about like having a constant like competition, like some leaderboards or scoreboards that kind of in a playful manner also drive in people that want to like just be very good at this kind of data? Have you thought about having such kind of leaderboards or such?
Yeah, no, that's definitely something we've been looking into. What we've been trying to do is leverage the the CVPR community, particularly that fine-grained visual categorization community. And they have this long-running relationship with Kaggle. And so we were going to evaluate after the second data competition if it would make sense to host like our own competitions through FathomNet and then maintain that activity. So we haven't done it enough for me to say conclusively that yes, that's something that we should do. Part of it is, funding as well. Like people like to participate in competitions. They love it if they are, there's like a purse or an award. And so that's not something we have budgeted now, but, over time, the hope is through this collaborative R&D program, Ocean Vision AI, we might be able to sustainably support those kinds of activities, including a reward or awards. So, but the idea is that, if FathomNet contains all sorts of data from a lot of different sources, that could be, UAV data, that could be, drones, AUVs, etc. There's a really great opportunity, right, for the computer vision community to look at how do they get their models to generalize well on such a wide-ranging data set. So we'll see.
That definitely makes sense, especially in the in times of like these really big foundational models. I think that's very promising to do. I was also wondering with respect to this community aspect of people being able to submit data, is it more so that, I mean, you mentioned that you mostly look for human annotations or human experts, right? Because this is the bottleneck, but in terms of people contributing data, is that do you also look for raw data, just data of underwater world, or is it more so that you would really prefer labeled data?
For FathomNet, we preferred label data. But the labels can be varying levels, right? We can't expect everybody to know, an animal down to a species level. But if you have it as a fish, then a fish expert can actually be pointed to that and then delve more deeply into the taxonomy. But so for FathomNet to work, it has to have labeled data. But what I think is interesting about this whole Ocean Vision AI approach is that there's data infrastructure that's being made to support and host visual data, even if it hasn't been processed yet, right? It's just like, I think there's so many different groups and individuals that collect visual data for monitoring that just don't have a good plan for how they're processing or utilizing that information. And so if we can help by making that data fair and accessible to the entire community, that's a good service, not only for the people who need to process that data, but also people who might be using the downstream data products as well.
That makes sense. Yeah. In terms of data modalities, is it mostly vision, video, or image data, or is it also other modalities? I don't know, let's say LiDAR or sonar kind of data of like
So that's a good question. We haven't had any LiDAR contributions. We've had groups reach out about sonar data. So FathomNet, the way it's been built, it has what we call different imaging types. So there's a field that you can select, and based on the community that you have, right, you can utilize some sort of, phrase, whatever. So what that means is that you can parse the data in FathomNet using that imaging type moniker. And so that's why, originally we were focused on underwater data because that's the kind of visual data that we collect. But there's lots of people doing biological monitoring in the ocean from drones. So FathomNet can accommodate that data. They would have to select an imaging type for, I don't know, drone or UAV, whatever they need. But the idea, like, the way FathomNet was built was so that it can be extensible and the data can be distributed. And so there's a lot of thought that went into building out that database and its longevity.
All right, that makes sense. Yeah, we'll actually have a featured paper talk right after you, which will also be about, I think they also feature a data set for underwater computer vision. So let's see, maybe maybe
Put it on
they
FathomNet.
exactly, yeah, maybe they're doing that now. All right. Are there any other questions from the audience? All right, if not, then thanks again, Kakani. I'm really looking forward. I'm really interested in how FathomNet develops. I hope it will grow big soon. And yeah, thanks again. And we'll go to the next program point. So the next program point, as teasered, is so first we are going to look at the submitted papers, and afterwards we'll look at the featured paper presentation that I just teasered. And yeah, for the submission spotlights, we will either play video or if you're there online, you can do the online presentation. And we'll start with Martin Tran, SafeSea, synthetic data generation for adverse and low probability maritime conditions. I think you're not there, so we've got to play the video. Correct me if I'm wrong. Right.
SafeSea synthetic data generation for adverse and low probability maritime conditions. This work is a collaboration between myself, Jordan Hermawan, Associate Professor Arnold William, and Professor Clinton Fox. Extreme weather events create formidable challenges for both humans and boats navigating stormy water. While search and rescue operations now employ computer vision, the difficulty lies in obtaining good data to develop robust models for marine object detection. Methods like using game engine and generative models such as stable diffusion have been proven could be used in generating synthetic image datasets. However, these methods have a restriction on the marine images output that they can produce. We introduce SafeSea method as a proof of concept in which we offer a simple yet effective approach to modify sea state level in maritime images. SafeSea retains crucial object of interest, producing training datasets for marine object detection by utilizing blended latent diffusion to edit the original sea images background while preserving marine objects. The output results are then classified into different sea state categories while ensuring the preservation of object of interest. With the application of the SafeSea method, we transform original images from the Citron Sea dataset into the SafeSea dataset, featuring stormy sea backgrounds and marine objects. Our results demonstrate the superiority of our method over the stable diffusion in painting and blended latent diffusion. Additionally, we highlight the challenges faced by object detection models when confronted with increased stormy sea backgrounds. You can find the method in our paper, and I will be available in the Zoom session. Thank you.
All right, thanks for the video. The next spotlight presentation will be by Georgios Savatraki, an automated method for the creation of oriented bounding boxes in remote sensing ship detection data sets. Are you there online?
Yes, I am. I will share my screen.
Yes, perfect.
Just a second. Oh. Okay, hello, my name is Yorgos Savathrakis and will present our work, an automated method for the creation of oriented bounding boxes in remote sensing ship detection datasets. In several ship detection datasets, the object annotations are in the form of horizontal bounding boxes or HBBs. The purpose of this work is to automate the transformation of horizontal to oriented bounding boxes or OBBs. That way, the amount of data that can be exploited by existing oriented object detectors is enriched, and in addition, using these annotations, we can create augmented versions of datasets that resolve the ground truth object's orientation imbalance. The model pipeline consists of the segment anything model, or SAM, a morphological closing, and a contour detection method. The images with their objects HBBs pass through SAM, and using prompt points in alternate diagonals as foreground, we can get the most accurate masks possible for each ship based on the respective segmentation score. However, the segmentation is not flawless, and issues like disconnected components are resolved by running a closing operation on the resulting masks using an elliptical structuring element. Finally, the largest of the processed blobs passes through a contour detection method, to which we fit the minimum area rectangle in order to get the final OBB. Using the generated annotations, we can create augmented versions of our dataset with either the same or increased number of objects. In both cases, the aim is to iteratively uniformize the orientation histogram of the objects in the dataset. Using benchmark ship detection datasets like HRSC 2016 and baseline-oriented object detectors, we show that by training them on the generated annotations, the detection performance is similar to that of the ground truth, and that by using the increased size augmentation, the performance is even increased for most of the detectors. In conclusion, the proposed work provides an automated transformation method from horizontal bounding boxes to oriented bounding boxes, and an augmentation method which increased the detection performance of baseline object detectors on ship detection datasets. Thank you very much for your attention.
All right, thank you, Georgios, for a very nice spotlight. We'll go to the next one. Lynn Cactien with CDCC. Are you here? I think she might be not here. I'm gonna play the video then.
My name is Lee. I'm presenting. Hi. My name is Lee. I'm presenting our method, CDRC, a video-based unsupervised method for dynamic change detection in unmanned surface vehicle. In our framework, we divide video into the same length window. Correct window, we input it into the similarity scoring component to compute the similarity mean and standard deviation of this window. Then the value of all window will be passed into a clustering to separate some into the synchronic or not synchronic classing. Here's the similarity scoring component. We use a script frame for serving computing. Then we use a projection model to check the potential feature from images. Then the feature could be paired at the input into the similarity score module. Finally, from all these score values, we check the mean and standard deviation for the next step. We trained MaCVi2 on public maritime datasets for projection model. Then we use the bottom level feature for similarity score calculation. For similarity score module, firstly, we divide each feature into a grid. Correct grid cells the same index. We rank top frequency decrease factor to get the number of overlap with decrease factor, and we compare it with the plateau data sim to determine the similarity score of two cells. Finally, the similarity score of two features is averaged by the similarity score of grid cell. Here's the setting about impairment. As the last step, we are coming with two clusters. Here's the quantitative result of our method. The precision, recall, and F1 score of all classes shows a reasonable and promising result of our method. Here's some qualitative results sampled from the testset. Our method has some 4 positive and 4 negative at the boundary of dynamic synchrony. Overall, our method predicts results similar to ground truth. Here's some main reason. Thank you very much.
All right, thanks for the video. Next one up will be Shaif Chowdhury. I believe you're here.
Yes, I'm here.
Can you hear me?
Yes, can hear you a little bit silent. Maybe if you can do it a bit louder, but yeah.
Yeah, I think I can see screen. Yeah, so this presentation is about active learning strategy using contrastive learning and K-means for aquatic invasive species recognition. This is a joint work at Baylor University with the Environmental Science Department and Computer Science Department, and the work is funded by Texas Parks and Wildlife. So let's get started and see what are aquatic invasive species. So there are aquatic species like zebra and quagga mussels that are not native to United States, and they disrupt the maritime ecosystems like the Great Lakes. And for these invasive species, data annotation is very costly because they're really there. And it is also important to recognize them when they're at the larva stage, because once they are adult, it's very. Yeah. And because of these, we propose an active learning strategy that can reduce the need for costly annotation and help develop models incrementally. So on the right, you can see a map of the United States with spread of zebra and quagga mussel. And on the left, you can see some images of invasive species larvae. Yeah, and these are the larvae that we plan to recognize. On the top, it's mostly non-invasive, and at the bottom, mostly invasive. Okay, so let's talk about active learning. Active learning involves iteratively selecting and labeling examples from an unlabeled set to incrementally train a model. So it needs a human annotator as a companion when training the model. So at each step, it selects a set of labeled data, and a human annotator will annotate them, and then they're used to train incrementally. So in our case, we propose an active learning strategy that combines supervised contrastive learning and K-means clustering. So with contrastive learning, we create representation for the unlabeled data, and then using K-means, we cluster the data, and we select the clusters that are furthest from the center. We select the data that's furthest from the center of the cluster, and that way we are able to select diverse representation of the data, and then those data sets are annotated by the human annotator, and then it's used to incrementally train the model. Okay, so here are the results of our evaluation on the invasive species dataset. So invasive species dataset is generally imbalanced because invasive species are rare compared to native larvae. And you can see that our algorithm outperforms other baseline methods like coset and random sampling and entropy, etc. Especially our results are really good in the low budget and data imbalance situation. Okay, so because invasive larvae is really there, an active learning process is very important for creating models. To sum it up, our paper introduces an active learning approach for invasive species larva recognition. Our algorithm combines contrastive learning and K-means to select highly informative and diverse samples. And with just 100 labeled examples and 100 during active learning, we get a balanced accuracy of 78%. It can also help fine-tune for different environments. So we collect data in different kind of waterways and different times of the day. So active learning can also help fine-tune models based on the environment. Yeah. That's all. And if you have any questions, please reach out.
All right, thanks, Shaif. Very impressive results with just 100 labels. Yeah, we'll go for time reasons right next to the last speaker, which is Emre Gülsoylu with image and AIS data fusion technique for maritime computer vision applications.
Hello. To make sure that I will finish on time, I will share my screen and play the video. I think that's safest option.
All right.
Hello, I'm Emre Gülsoylu, and I'm going to present a technique for image and AIS data fusion to be used in maritime computer vision applications. There are various ship detection models, and deep learning approaches work very well for ship detection. However, they do not provide information like the location or speed or the dimension of a detected ship. It is, of course, possible to train deep learning models in a way to provide such information, but maritime computer vision datasets are scarce in general. The good thing is that the information like the type, course, and dimensions of a ship is present in AES messages, so a system that can fuse bounding boxes with AES messages can be useful for creating an information-rich dataset. To create such dataset, images are collected for 6 months from surveillance cameras located in various places in Hamburg around the river Elbe. And because of this broad time period, various weather conditions and different ship encounters can be observed. After various pre-processing and filtering steps, the fine-tuned YOLO V5 model takes an image and provides ship detections as bounding boxes. Meanwhile, homography-based coordinate transformation takes AES messages and predicts their coordinates in image space. After fusing the closest predictions together, an annotated dataset can be obtained. These are the results for individual cameras. Compared to other frameworks, our framework overperforms others for fixed cameras, and if we include panning cameras, overall accuracy is still comparable with other frameworks, while our framework being capable of fusion with non-static cameras. So in conclusion, we developed a homography-based fusion technique for associating bounding boxes with AES messages from images taken by static cameras and panning cameras. The dataset and the paper are publicly available and can be accessed via this QR code.
All right. Thanks, Emre. Thanks, Emre. I guess it relates also to what I asked Daniel from maritime robotics. So definitely an interesting topic. All right. We'll go on to the last part of the workshop, which is a featured paper presentation from Nisha. The talk is about a paper that was submitted to ICCV. And I thought it might be a good idea to feature that just to get like also some new papers from other conferences in here. And Nisha, you will talk about molecular underwater depth recovery. And yeah, hi Nisha.
Hi.
Do you mind sharing your screen?
Yes, yes, yes. Am I audible?
Yes, we can hear you and see the slides.
Okay. So thank you for giving me this opportunity to present our paper. So I'll be presenting our ICCV 2023 paper, Self-Supervised Monocular Underwater Depth Recovery, Image Restoration, and a Real Sea Video Dataset. So myself, Nisha Varghese, I am from IPCV Lab from Indian Institute of Technology, Madras, India. So our paper deals with depth recovery and image restoration simultaneously from a single underwater image, and we are proposing a real sea video dataset also. So the objective is to get a depth map and a restored image simultaneously in real time from a single underwater image. So this is one example of our output. So the first image shows the input image, example input image from our proposed dataset DRUA, and the second image shows the depth map obtained from our network, and the third image shows the restored image from our network. So these two outputs, depth as well as the restored image, are obtained simultaneously from a single underwater image. So the motivation for this work is the existing underwater depth estimation methods either use cues from haze or geometry. So haze has some depth information, right? Then geometry has also depth information. But both the cues from haze or geometry are not being used by any depth estimation methods, but we are using that. Then there is no deep learning based network which simultaneously outputs both depth and restored image. Then for supervision, there is no real pair data for underwater image restoration. Then for utilizing geometry, we need underwater video datasets, but there is no underwater video datasets. So in order to meet these requirements, we propose our network useReadyNet, which uses cues from both haze and geometry for underwater depth estimation. And we simultaneously outputs both depth and restored image from a single underwater image. And in order to avoid the full supervision, in order to avoid the real pair data for supervision, we are using self-supervision only. So our network uses only the input underwater image for training. And we captured and proposed a real underwater video dataset, so from which we can use the geometry cue for depth. So our dataset is known as DRUA. So coming to the state of the art for underwater depth estimation restoration, it can be classified as traditional prior-based methods and deep learning-based methods. For traditional prior-based methods, they use some priors for finding the depth or restored image, but there can be prior mismatches that causes incorrect parameter estimation. For deep learning-based methods, that can be classified as zero-shot method, supervised, and unsupervised or self-supervised methods. Zero-shot methods is very time-consuming, and the next one is supervised method. For supervised method, real pair data should be there. But in the case of underwater images, it is difficult to capture the real pair data. So the best choice is to use unsupervised or self-supervised method. So that is our approach. Our approach is a self-supervised method. So this is the block diagram of our approach. Here I1 is the underwater image and I2 is the next underwater image in the same video. Then I1 underwater image will be disentangled into its components. So I1 is the input underwater image that will be disentangled into its components A1, J1, TD, TB. So what are the components of I1? So we are using a revised underwater image formation model that is given here. So I is equal to J TD plus 1 minus TB into A, where I is input underwater image, J is a restored image, TD and TB are transmission maps corresponding to direct signal and backscatter respectively, and A is the global background light. So actually we are splitting this underwater image to its components J, TD, TB and A like this. Then those four components will be combined here to get this I1 reconstructed image. So ideally speaking, I1 reconstructed and I1 should be equal. So this can be used for the first cell supervision. And we are using, and the transmission map and the depth are related by this equation. Transmission map is equal to exponential of minus beta d of x. So depth is here and transmission map is here. So we know transmission map. So we have disentangled the transmission maps from here. And so from transmission map, we'll find depth analytically using this equation. So we'll get the depth here. Then we use the next underwater image in the video, I2. Then using the same SRNet, we'll find the clean image J2. So from this equation, we can find that J is the clean image, right? So from A2, we'll find J2. J2 is also the clean image. So J1 is the clean image corresponding to the first image. J2 is the clean image corresponding to the second image. And we find the pose between J1 and J2 using a PoseNet. So we have the pose here and we have the depth here. And using this depth and pose, we warp J2 to obtain J1 here. Then J1 will be, so this J1 dash and this J1 should be ideally equal. So this can be used for the next cell supervision. And we are warping I2 to I1 also using the PoseNet, using the same pose and depth. Because the input geometry should be equivalent to the output clean geometry. So here we are warping I2 to I1 dash. So this is the next cell supervision. Here we are using the haze cue is inside here in this block because this is the haze equation. So here we are finding depth from this haze. So we'll find the depth here and this depth will be refined using this geometry between I1 and I2 using this warping. So this is our concept. So for this, we are using different losses. First of all, we'll split the input underwater image to its components, and we combine those components to get the I1 reconstructed image. So between I1 reconstructed and I1, we'll find the first loss. So this is our cell supervision 1. Then for the next cell supervision, we warp J2 to get J1 dash, and we compare J1 and J1 dash. Along with that, we warp input underwater image I2 to I1. Then we find the difference between them for the next loss. So this is our cell supervision 2. And for depth smoothness, we are using depth smoothness loss. And channel-wise depth consistency loss is used to obtain a single depth from every transmission map channels, because for underwater images, transmission maps corresponding to red, green, and blue channels will be different. So during testing, we need to use only 3 blocks: SRNet, TMNet D, and BetaNet. So we'll pass I1 here. SRNet will give the restored image J1, and TMNet will give the transmission map. And using beta, we'll find the depth analytically. So this is our testing. So both the outputs, the restored image and the depth map, is obtained in just 18 milliseconds. So this is one sample output. So the first one shows an example video segment from our proposed dataset Dhruva. And this is the clean image, and this is the depth map. Here, depth map shows the near portions are brighter and the far away portions are darker. Then about our dataset, proposed dataset. So it is a first ever underwater video dataset, and it contains video sequences of 20 artifacts. Artifacts means rocks inside the sea, and we have a 360-degree azimuthal view of every artifact. So we have such 20 different artifacts are there. Here you can see the 3D point cloud. You can see of each of one example, an example 3D point cloud you can see here, and this is the camera path shown. Actually, the diver goes around the artifacts for every artifact. So it can be used for underwater 3D reconstruction, underwater nerve, video interpolation, extrapolation, etc. These are some example results for some images collected from internet. So this is the depth map, and these are the restored images. Here also some underwater images, and these are the depth maps and restored images. And in the paper, we have included a dense comparison between the state-of-the-art methods. So you can refer that. The conclusions: our method is fully self-supervised, where only input underwater images are used for training. And we utilize cues from both haze and geometry for depth estimation. And we returns both depth and restored image simultaneously. And it performs very well. And the computationally most efficient, both outputs in just 18 milliseconds. And our proposed dataset can be utilized for view synthesis using NERF, underwater 3D reconstruction, etc. Thank you.
All right, thank you, Nisha, for a very visual, nice talk. Are there any questions from the audience in Zoom or here? Otherwise, I will ask some question. So your method is it looks pretty sophisticated. I wonder, I mean, it relies on the haze, you said, but I wonder if a similar method could also be applied to general depth estimation, like not just for underwater, but for any kinds of scenes. Do you think this is easily possible, or?
Yes. Actually, works are there for finding depth for surface images, but they aren't using the haze information from the image. So it is clean image, right? So they're using adjacent images from a video for training. So for surface images, instead of using this haze, so here we are using haze plus geometry, but in surface images, people are using only the geometry between the 2 frames.
Okay, that makes sense. And I'm not an expert on depth estimation, but I wondered in how far the depth of field plays an influence. Is that a thing that needs to be considered here as well, or not?
A depth of field.
The depth of field, so like how sharp individual points in the image are, right? Sometimes my background now is really unsharp, but this is a virtual thing, obviously. But depending on how you set the focal length, right? Certain things are sharp and other things are not sharp. Is that a thing that you considered or needs to be considered in this case, or?
Okay. So actually, we have not considered this depth of field concept here. So we are using our own captured data for training and testing. We are using other data sets also.
Okay, and when capturing the data, is there any consideration that needs to be done in terms of depth of field or something like that, like focal length?
Okay, that I'm not sure.
Okay, no worries. I also wondered, so just because we had FathomNet, Kakani talking about FathomNet earlier, and you creating also a data set. Generally, what have you considered integrating your data as part of FathomNet, or have you heard of FathomNet, or what's your knowledge of that?
Actually, it is an independent data set.
Sorry?
Hello?
Can you just repeat what you just said?
No, I have not integrated it to FathomNet.
Okay. Is that a thing you would consider, or is that something like you knew of?
No, I haven't. I have heard about it.
Okay, all right. I was just trying to get an idea of like how familiar people are with that, but all right. Thank you, Nisha, again for your really nice talk.
Thank you.
And yeah, I guess that brings us to the last section of the workshop, which is the thank you part. So I'll be quick, I promise. Yes, so we had a really nice workshop, but obviously this would not have been possible without the help of many people involved. So first of all, thanks to the other organizer, Loise, Mate, Janis, Mattia, and Arnold. And especially for the program and technical committee that helped preparing the submissions for the papers and also reviewing the papers and also setting up some of the challenges and competitions. Thanks to these guys as well. Thanks to the people that provided a technical report on their methods. So people that participated in the competitions. And also, of course, thanks to the sponsors, Sentient Vision Systems and Luxonis for providing prizes for 2 of the competitions, and also for Lookout on providing the data set. Yeah, so this was roughly a 5-hour workshop, and yeah, we'll look forward to future iterations. You can stay excited. We have already plans for a 3rd iteration, but it's not really concrete in the sense that which conference it will take place in. So Hawaii has usually been a nice location, but it's also very far away for Europeans. For Europeans, it's like 4 a.m. right now. So for whoever European that stayed that long, props to you. But next year, MaCVi will actually be in Arizona. So that's a bit better, let's say for Europeans at least. But yeah, we are also thinking about other conferences that are maybe more Europe-centric, but this is not really clear yet. Are there any questions from anyone in the audience? Any comments, criticism? If not, I would conclude the workshop. We will go over in person to this other room to have a short poster session. But yeah, you can also stay here virtually if you want to exchange some information. I'll leave the Zoom room open. And yeah, thanks again. And have a nice morning or evening. Bye-bye.
Hello, Georgos. I have a question. So,
Hello, Emre.
yeah, thank you very much for your presentation. I wonder if you fine-tuned or trained some models on your data set and used other data sets to test, to measure how your method works on different data sets.
Right. So thank you very much first for your interest. I'm glad you liked it. Actually, the idea was not that our work is a detection model per se, but essentially a transformation method between horizontal to oriented bounding boxes for existing ship detection datasets. So the idea is not to create a method which outperforms other detection methods, but examine whether automatically created oriented bounding boxes can yield similar performances to manually annotated oriented bounding boxes. So the main point was to show that using automatically created oriented bounding boxes, we see similar performances. So that means that one shouldn't really bother himself with manually annotating objects, but he can use that method to have these annotations created automatically. And actually, this method, this application per se, was very suitable for that task, because if you see ships from satellite images, you can take advantage of that elongation that these objects have. So if you noticed in the presentation, one of them, the first part was the segment anything model, which can take an arbitrary number of input prompts, either as points or as horizontal bounding boxes. But if you use one point, which in several other applications, people who do similar works do that. If you do it in this scenario, it doesn't really work. It clatters with the background. The segmentation is not really qualitative. But if you take advantage of the elongation of the ships, you can put points on the diagonals. It is sure that since the ship is elongated, its axis will be along one of the two diagonals. So you use foregrounds in one diagonal, you get a score. You set the foreground points on the other, you get another score. And the one which gives you the higher score means that the ship is on the diagonal. So you know where to calculate the mask in order to get the final oriented bounding box. If you do that, you can use these annotations to train existing object detectors to see how well the method, this method of annotation fares. And the argumentation that was used essentially led to increased detections for the existing object detectors. So it can not only create automatically the annotation data sets, but you can also use it to create augmented data sets essentially for free, because it annotates the images automatically.
I see. Thank you very much for your detailed answer. Yeah, now I understand even better, and I will read the paper thoroughly. Thank you.
Thank you very much. Also, I had a question for you.
Okay.
If I remember correctly, you mentioned in the paper that you combine inputs both from camera and from AIS. And from what I understood, the idea was to make predictions not only about the bounding box, but also location and speed.
Yes. So
Could you, I got a little lost there. Could you explain to me a little better how the IIS can be used to predict speed?
okay, so first of all, maybe I can share my screen. Let me see. Oh, here. So let's go this one. Is it visible now?
Yep.
So there is one figure here that I want to show you with the method called homography. You can transform the coordinates from image coordinates to world coordinates or vice versa. So one way to associate AES messages with the bounding boxes is the location that that vessel at a specific time. So if you can transform, or if you can predict the location of the ship by just using the AES message, since it includes some other information like speed, course over ground, dimensions, etc., and many other, you can associate that message with that bounding box. For example, if we used your approach and use satellite images or SAR images, we could have an idea about the course of the, not course, but heading of that ship. So heading also could be another value for us to associate AES messages. Actually, we are also working on that. We are trying to predict course over ground or heading of the ship based on RGB images taken from some cameras, not satellite imagery or any other remote sensors. Yeah, perhaps after I read your paper thoroughly, we can. I will send you an email if we can collaborate on something together.
Oh, okay, sure. So from what I understood, essentially one can take the data from the AIS, which has information about location and speed, and then you can you can map that into a camera field, which can tell you the bounding box. You can correlate the location to that bounding box. So that can essentially be also used for tracking.
Yes, you can also do that. Yeah, definitely. You can do that.
If you have a prior knowledge about the speed, my guess is that you can use this information to have an expected location of the ship in question at the subsequent image frame.
Yes, yes. You can definitely do that. Or you can even make it more complicated and try to predict the trajectory from the AES data and have more predictions, as you said. That can definitely be, it's definitely possible. Yeah, for example, here, the prediction, this red dot, I'm not sure if it's visible for you, but
yes, I can see it.
Red dot is actually our prediction that comes from AES message. As you know, sometimes AES messages contain data that is not reliable because of the GPS sensors, etc. for example, these ones are almost spot on. At least they're on the image, the ship image, this tugboat image. But this has some problem apparently. But even then, it can be associated. This is the orange one is the center of the bounding box that's detected with our fine-tuned YOLO V5 model. And then we can get this association, and we know more about this vessel.
Okay, I see. Well, it makes sense because the one that you're showing now with the cursor is the one that's most probably moving. So by the
Yes.
time the AIS signal gets sent, in real time, that object will have moved on. So yeah, I guess I understand why this mismatch may happen.
Yeah. And this is one of the extreme ones. For example, here, it's very close to each other, the red one and the orange one. And our YOLO model couldn't detect anything here, but there is one AES right on the vessel. Yeah.
I see.
Okay.
Thank you for your information as well. I find it a really interesting application, actually.
Yeah, the main contribution actually comes from that we applied it to also panning cameras, panning surveillance cameras. So the results are as expected worse than fixed cameras, but still comparable. So
yes,
yeah, we are going to share the data set publicly very soon.
Okay. So I'll stay tuned then. I'll also
Yeah.
take a look at your paper as soon as I get the opportunity.
Mm-hmm. Okay, then. I wish you a good day and a good morning, actually. Yeah.
If it is a morning for you as well, I wish you a good morning too then.
Yeah. Thank you. Then, yeah. Bye-bye.
Bye. Thanks.
Bye-bye, Benjamin. Thanks for the organization.
Okay. How do you guys like it, or what's do you have some criticism that I can take away?
Actually, this is my first publication ever.
Okay.
So this was my first experience.
That's
I
cool.
found it really cool, really informative. I think every single part of it had a really informative topic to talk about, from the keynotes, from the featured presentations. And I like the fact that many different aspects were taken into consideration. I mean, everything from airborne to USVs to more practical applications like how to embed detections. I mean, underwater scenarios. I think the fact that this workshop covered literally everything actually was the main, actually one of the most important advantages, because it can give information and insights to different domains, things that somebody else may not have even thought about at all.
Right. Yeah,
So,
I'm happy you liked it, and it's really nice that you're already that engaged with your first appearance, let's say, in the workshop. That's cool.
Yes. it was an extremely amazing experience. I mean, despite the fact that over here it is already 5:30 a.m.
Oh yeah, the whole night. You can see probably now.
Yeah. That's what I'll most likely do. It was definitely worth the staying awake up to now. I mean, it was really amazing. So thank you very much, honestly, for this organization.